Welcome to APEC Open Mic. It is August 17th, and I'm your moderator, Tim Ventura. I want to give a big thank you to everybody who's joining us on today's call, along with everybody watching us on YouTube. So as a reminder, today's session is for open discussion and ad hoc presentations. We're not scheduling presentations in advance. We do have a couple of folks who I am hoping are going to give us some updates. One of those is Jarod Yates. Jarod and I were actually on a trip to Reno a couple of weeks ago, and we found some interesting stuff about Dr. Friedwardt Winterberg. And I am also hoping that James Woodward and Curtis Horn give us an update and some of their latest runs. I saw them, let me see, about 3-4 weeks ago now, and they are doing absolutely amazing work. And then we have a lot of other stuff going on as well. Mark Sokol got a new microscope, and he is doing in-depth analysis on Art's parts, as well as continuing work on his DNP stuff. So we have a lot of stuff going on, and that is just what I know about in terms of the labs that we usually work with. You can view conference replays, details, and speaker info on our website at altpropulsion.com. During the ad hoc presentations, please try and save those questions for after the presenter when they finish. We're trying not to enforce, too much structure there. So you can jump in if you feel it's appropriate. Just try not to interrupt. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. And I'm going to do admit all there real quick. Okay. And you can also type your questions into chat. We'll try and get those as they scroll up. Mark Sokol is here today with me. He is going to be my guest host. He's going to help me with this because we have a lot of stuff going on. So one of the changes that we have made is we're asking everyone to have their camera on, and then, of course, the microphone off unless you're speaking. And the camera on is so that we can do introductions. We're going to go through and just brief, right? Like we're talking 15 to 30 seconds, who you are and what your favorite project is today. I think that's probably a great place to start. So that's kind of where things are starting out. And let me take it off Spotlight. I will put it on, let me see. Put it on gallery view, actually. There we go. And I think we are all set. Okay, so let me see. If folks can unmute themselves. Hopefully I've got this all set up correctly. Why don't I start with Mark Sokol? He is in my top left screen. Sir, brief intro.
Okay, Mark Sokol here, Falcon Space. I'm in Hawthorne, New Jersey, working on anti-gravity technologies of varying types. As you can see, I put on a timer for myself. This is going to be for everyone as well, just to keep everyone honest and keep everything flowing.
That's awesome. Okay. Okay, well, let's go. Let me see. Let me go to Dr. James Woodward next. Let me see, Jim. Let me ask you to unmute there.
Hi there, Jim Woodward. I've been in the business a long time. Maybe you've heard of me. Curtis and I and Michelle Broyles, primarily, along with Paul March, David Jenkins, Chris Obafunwa, David Mathis, are working on so-called Mach effects, breast mass fluctuations that can be induced by accelerating something while its internal energy is changing. I've got some results from today to show you. Curtis, I'm going to, is Curtis on, Tim?
Yeah. Well, Jim, I am not sure. I don't think he's on quite yet, but let me come back to him. We're going to run through our introductions real quick, and then I will come back to you guys for updates.
Okay. I will doubtless use up my 30 seconds.
Thank you, sir. Thank you. Okay, let me go to Drew in sunny Florida.
Drew, sunny Florida, about 30 miles north of the Kennedy Space Center, working on asymmetrical electrostatic propulsion along with Dr. Charles Bueller. And we've got a update if anybody wants to hear it later in the program.
Awesome. Thank you, sir. Let me go to Dennis Lee next. Dennis, welcome back, sir.
I actually didn't know whether I would be here today, but I have a short attendance for this conference. But anyway, Dennis Lee, a former NASA employee at Goddard Space Flight Center. I say former because I finished up my task last week on that. So I'm 100%, pretty much 100% time on my NSF work, which is propellantless cam drive is what it is. I presented to AIAA 2 weeks ago successfully. It was a really good session, but I look forward to our discussion.
Thank you, sir. Let me go to HFK next. Welcome back, sir.
Thank you. Henry, and I visited my local drug dealer and got one of these last night from Micro Center. Protoboard. And I'm going to be tinkering to see if I can let the smoke out.
Wonderful. Wonderful. Thank you. Let me go to Zoltan next. Welcome.
Thank you. So my name is Zoltan. I'm originally from Hungary. I do travel a lot between Hungary and the US. Right now, I'm actually from near the Croatian-Hungarian border. These days, most of my times are taken up by technical investments in the stock market. I will drop in the chat. I have a big pocket of investments in two companies in IonQ, which is dealing with quantum computing. And the other one is Intuitive Machines, the guys who sent up the moon spacecraft this February. My major interest in physics, and as I said it like 2 occasions ago, I did my thesis in slowing down the speed of light about 18, 20 years ago.
Wonderful. Thank you. Thank you, Zoltan.
Thanks.
Okay, let me go to Mikolaj next.
Hi, my name is Mikołaj. I'm new to this thing. Basically my professional is I'm designing ASICs. Okay, nothing to do, but I figured I have an idea about pushing against quantum foam, which I'm trying to vet, and I would like to talk to as many people as possible. I had some input from David, and I would like to basically continue my testing. The idea is strange. I'm really skeptical, but the test results are positive. That's why I'm here.
Wonderful. Thank you. Thank you. And yeah, pushing on quantum foam is that is a major idea. So I'm all for that. Let's get into that later. Let me go to Brad next. Yeah, go for it, Brad.
Hi, I'm Brad. I'm from Northern BC, Canada, and I'm just a fanboy. One of you is the real life Zephram Cochrane, and my future self would regret not seeing this progress. And my favorite project is the Aurigema drive.
Ah, wonderful, wonderful. That is not. I'm not the Zephram Cochrane. It's probably Mark, but yeah, not me. So, let me go to Michael Boyd next. Michael, welcome back, sir.
Thank you. Hi, I'm Mike Boyd. I live in SoCal, California. That's SOQUEL, not Southern California. And I've been I wrote a paper resolving the extra dimensions for gravity. Basically, I did some experiments and found that gravity was strong close up, and there were 2 forms of it. My paper published a couple of days ago in the IEEE Sensors Journal. And so I'm just kind of celebrating that. Took a long time. So.
Awesome. Well, thank you, Michael. Thank you. Let me see. Let me go to Richard L next. And I don't see. Oh, there we go. Okay. Hey, Richard. Welcome back, sir.
Okay, make sure I'm not muted this time. So, yeah, mechanical engineer. I'm working on solving free energy. I also am getting pretty interested in this propulsion. I did build propulsion device. So, and I do have an understanding on UAP, you know, stuff that I read like 20 some years ago.
Awesome. Okay.
Yeah.
Well, thank you.
Yeah.
Thank you. Let me go to Eric Ryder next. Uh-oh. Wait.
Oh, what happened?
What? Mark's timer reset. It reset to the grandstand music. Put it back on beep. Let me go to Eric Ryder next. Eric, welcome, sir. Eric is going to be doing a presentation on August 31st also. Yeah, go for it, sir.
Good. Well, yes, Eric Ryder. I'm from Pacifica, California. I have experiments that refute quantum mechanics. And what I'd like to do is quickly later here to show like a slide from either of two lectures. I have two different kinds of lectures. One that emphasizes the history of quantum mechanics and like how did it go wrong. I can explain that because what I have is very controversial. The history look at it is important, or I could do it from the standpoint of the experiments. So I'd like to ask your group which way they would like to hear my lecture.
Yeah, well, and yeah, later on, if you want to run through a slide or something like that, that would be great. And again, August 31st, I think I've got you on the schedule. I'm working on that. In fact, that's after we get done tonight, I have to go get that page published. So let me go to Ken L next. Ken, welcome. Oh, you're muted, sir.
All right. Can you hear me?
Can now. Yep.
Yeah. My name is Ken Lentz. I'm sort of new to the conferences. I'm working on a couple of presentations that I'll have to run by and see if anyone's interested. I'm in Huntersville, North Carolina, down by Charlotte.
Awesome. Ken, thank you. Thank you. And thank you for, I know you've been collaborating with some of the guys too. So thank you for that as well. Let me see. Let me go to TCTIN.
That would be me. My name's Trevor. Sorry about that.
Hey, Trevor.
Tag. I'm a PhD candidate at William and Mary. I do not work in advanced propulsion. They don't offer that as a research option. I'm in cold atom trapping, but I would say late in life, James Woodward's work very much inspired me to go to college and get me to where I'm at now. I would like to be able to work in advanced propulsion once I have that PhD in hand.
Wonderful. Wonderful. And I used a little known feature to rename you Trevor in the.
Oh, thank you.
Yeah. Yeah. Well, thank you, sir. Let me go to Brendan next. Brendan, welcome back, man.
Hello, everybody. Yeah, my name is Brendan McNamara. I live in the Pacific Northwest. I'm very interested in active discussions with people, Daniel Davis and a few others about space-time metric engineering, gravity modification, kind of looking at all these things and trying to consolidate them. As far as projects go, I'm most excited about Curtis Horn and Jim Woodward's work, as well as especially Andrew Aurigema and Charles Buehler. Pretty exciting stuff.
Awesome.
Thanks for having me.
Thank you, Brendan. Let me go to, go to JH next. Sir? Let me click ask to unmute. Sorry about that. There we go.
Hi, my name's John. I'm in the Seattle area and have many similar interests to Brendan in we're trying to organize a APEC book club of sorts to review patents and electrogravitics and in theories like that. Yeah, that's my story.
Awesome. Well, thank you, John. Thank you and welcome. Let me go to David Chester next. David, welcome back, sir.
I'm David Chester. I'm a theoretical physicist. I got my PhD in 2018. I fell in love with quantum field theory, and now I'm kind of looking back at more controversial claims free energy, alternative propulsion, and just trying to see if it can fit in with the modern experiments, because there's kind of this bifurcation. If we go back to these ether ideas or something like that, then we also need some framework that can actually match all the experimental evidence. So I'm kind of looking into quantum electrodynamics and trying to see how far that can be pushed towards some more controversial claims and see what's different. Thanks.
Wonderful. Thanks, David. Let me go to Jarod Yates next. Sir?
Yep, Jarod Yates, Pacific Northwest. I have been working on Alexei Chekhov's Graviflyer for a while. I've worked on a couple other alternative propulsion ideas that deal with field interactions. I am very thoroughly obsessed with the flying triangles and trying to understand government reverse engineering efforts, specifically engineering efforts that occurred during the late 70s to the early 90s. That is my primary focus. So anti-gravity and UFOs, this is our tribe, right?
Yeah. Well, Jarod, thank you. And just as a reminder for everybody, Jarod conned me into going to like high altitude Reno last week. So he had this cushy task. He was scanning papers. He was kicking back margaritas. He was chatting with Winterberg's family. And I was like hauling boxes in like 150-degree heat. It was horrible. So that was last week, but he found some good material. And so I'm hoping he could share some with us today. Let me go to Ryan Wood next. Sir?
Well, thanks, Tim. Ryan Wood, I'm in Colorado. My day job is the CEO of Electric Fusion Systems, but I've been interested in gravity and working on a review of a variety of gravity projects. I have deep expertise in crashed UFOs, written several books, and I'm looking forward to engaging more with your group.
Well, and thank you, and welcome back. And trust me, we will have you on for future presentations. So let me go to Rick Muller next. Rick, welcome, sir.
Oh, thank you, Tim. My name is Rick Muller. I live in New Jersey. I like to come on APEC. I came on 3.5 years ago. I haven't met a session. Have not missed a session. I meet a lot of people here, and I like to talk to them about anti-gravity, basically. I like all the presentations on anti-gravity. I talk to a lot of people around the world about it. And that's about it.
Well, Rick, thank you. Let me go to Dan Ravisto next. Dan, welcome.
Well, thank you. I'm just a supporter and lover of expanding the brain. Being 52 years ago, a math major, I didn't get much use except in the finance world, which is what I do. So I come here to have Mark and Drew and Jarod keep my brain fresh, making my dreams back 50 years ago come true with what you guys are doing. So I'm just here to support and keep my brain fresh. How about that?
That's awesome, Dan. That's awesome. They keep my brain fresh too. So I'm right there with you. Let me go to Leonardo next. Oh, let me ask you to unmute. Leonardo, welcome, sir.
Okay, Leonardo, I'm Leonardo Rivera. I'm an independent researcher. I'm working in the idea of a mechanical propulsion system, and the idea is based in two bodies moving in the same direction, and at the same time they are moving in opposing direction.
Wonderful. Leonardo, thank you so much. Let me see. Sorry, Zoom is shifting things around on me, so I'm not. Let me go to Kurt Jonach next. Kurt, welcome.
There you are. Hey, Tim. Okay,
hey.
So I am joining you guys my name is Kurt Jonach, joining you from Silicon Valley today. I've been listening in a lot of times, and I'm like Rob, I just support you guys. I like what you're doing. I do experimentation myself in the field of AI, which is very different from what you guys are doing, but I love listening in. And Tim has great guests. Like I know, like Ron Wood. I mean, I've been familiar with him, and then some of the other people he's had on. So I just listen in. I just support you guys. Okay.
Wonderful. Well, Kurt, thank you. So I mean, you've been in this area forever, right? In fact, you had the X Prize team way back when.
Yeah. I've known you since you were doing you had anti-gravity or something, and you were doing these great experiments, and they're just, you know, it's just, yeah.
Yeah. Well, no,
Exciting, yeah.
we'll hear it for the old timers. We're old
That's
timers
right.
now. So
That's right. We're old time.
let me go to
Thank you.
House CC. Hal, are you there?
Yeah, hi.
Hey, can I ask you to turn your camera on, sir?
The thing doesn't work. It's just an old computer, and I'm too cheap to replace it. So I'm in the Midwest, and I'm here to get some more insight and to see what's going on in the current propulsion field. We'll have some questions later on. So thanks for having me here.
Oh, absolutely. Let me go to Richard Bandurek next. Richard, welcome. Welcome back.
Oh, thanks. I missed a couple of these. No, I'm just a researcher. I'm doing research in extended electrodynamics. I got a number of grants. I'm on a bunch of committees for the government to just study this science. So, yeah, I'm just here to be a fly on the wall and just to see what everybody else is doing.
Oh, that's wonderful. That's wonderful. Well, thank you so much for coming back. Let me see. Let me go to Darren next. Darren? And could I ask you to turn your camera on, sir? Ah, there we go. I see him over in the corner. Oh, you're muted still, sir.
Yeah, I'm just an old retired guy, and I like interesting things, and I find a lot of interesting things on your show. So thanks a lot, Tim.
Oh, absolutely, Darren. Well, welcome. Welcome. Let me see. Let me go to Gary D next. Gary, let me ask you to unmute.
Can you hear me?
Yeah, I think Gary's having some camera issues today also. He emailed me before the call.
Yep, can you hear me?
Yep, I can hear you, Gary. Can you introduce yourself?
I'm Gary, and I'm just here to listen to you guys. You guys are the experts, not me. I find this fascinating, and I'm here to learn. That's all I can say right now.
Well, Gary, thank you. Thank you, and welcome. Let me go to Lulu next. A person who needs no introduction. Lulu has been in our conference. Lulu, welcome, ma'am. You have been with us for ever and ever and ever.
I have. I love APEC, and it's like I make time for it. You know, there's nothing could stop me. I don't care what I'm doing. I just step aside. I turn on my camera. It's APEC time. Everybody, be quiet. I need to listen. My name is Noel. I live in Texas. My background is medical business management. I'm a licensed agent in the state of Texas. I'm interested in astrophysics and space and future tech.
Awesome. Thank you so much. Let me go to Randa next. Randa, welcome, ma'am.
Hey, hi, you guys. Nice to see everybody. And I'm Randa Milliron. I'm the CEO and co-founder of Interorbital Systems. We're here at the Mojave Air and Spaceport, where we've had a program going on for the last 27 years with bipropellant liquid rockets. But we're very interested in doing atomic rockets and interested in partnering with anybody who might like to do that. We're getting a launch license currently for our bipropellant liquid orbital vehicle, hopefully to launch within the next 12 to 15 months. So living it up out here.
That's exciting. That's exciting. So in terms of atomic rockets, the first name that comes to mind is Jarod Yates. So he would be someone to correspond with because he is digging into that right now. And they're actually, if you want to email me, Randa, I think you have my info, right? Yeah, just shoot me an email and I can connect you with some folks. Let me go to Isaiah. Let me go to Isaiah Ritchie next. Isaiah, welcome, sir. And I'm hoping, just so you guys know, I'm hoping to go visit Isaiah in October. He is doing some amazing things with his SEG, and then he's going to be building another ring for it as well in the next year or two. So
excellent. I'm looking forward to that. Hello, everybody. My name is Isaiah Ritchie. I live here in Newburgh, and I'm not a scientist, but been studying the SEG for 15 years and working on a fairly, as accurate as can be, replica of it. And hopefully next year be endeavoring to do the second ring, and I've already gotten some pretty amazing results, including like one of the rollers levitating across the surface as it spins, the sound reducing, and a small amount of voltage coming out of it. So yeah, happy to be here.
Awesome. Isaiah, thank you. Let me go to Steve Carman next. And I think Steve might be having some, because it keeps saying admit, admit, admit. So Steve, if you can talk, please do, but I'm not sure. Okay. Yeah, I think his is kind of stuck. So we'll skip him. And we'll just see, maybe he can make it in later. Let me go to Gabriel next. And can I ask you to turn your camera on, sir?
Hi.
Hey,
Well,
welcome.
Yeah, I am from Brazil. I am an independent researcher. I am very interested in the extended electrodynamics and its implications to technology in the fields, for example, alternative propulsion, healing machines, all these things. So it's me.
Awesome. Thank you so much. And last but not least, let me go to Mr. Ron Evans. Ron, welcome. Ron is an old timer also, in a good way, in a very good way. Ron, are you with us? There we go. Okay, it looks like Ron might be having some microphone issues. Okay, well, I think that's it for now. Everybody, welcome. I love running through these introductions. I'm going to blame this firmly on Mark, but this is, yeah, and he set the timer up too, so that is awesome. I love doing the introductions because we have a community that we're building, and one of the things that I've seen is over the last couple of years that we've done this conference, it is maturing. It is going from being just, it was almost like a house party, and now it's like becoming a professional organization. It's a professional community. And so one of the things that we're trying to do is just help increase that and kind of go with that. Oh, there's Ron. Ron, welcome, sir.
Hello, how do you do? Sorry, I always have problems with computers. So I'm Ron Evans. I'm ex-BAE in the UK. It's midnight here, so I'm ready for bed.
Yeah, well, thank you for joining us.
Well, I wouldn't miss it. My interest is I gave a presentation back in 12th of March, was it? 12th of March 2022. I've been having another look at it, and I'm still interested, and I wonder whether any of your colleagues would be willing to have a look at it too and help me.
Yeah, well, I would love to have you present again, and if you want to send it, Ron, do you want to just shoot me an email and I can forward it out and ask folks?
Okay, I will do.
Okay, yeah, absolutely, absolutely.
Thank you for inviting me.
Yeah, and we had one more person. Let me get Biaza Steinmetz. Biaza, welcome.
Thank you. Good to be here. Very interested in what you're doing.
And thank you as well, sir. Okay, well, let me see. So yeah, again, that's it for introductions. I am super excited. So things are kind of casual and informal. And again, let me see, Alt Y on Windows or Option Y on Mac if you want to raise your hand. I'm not sure if anybody has any presentations. We did have Curtis Horn at some point. When Curtis arrives, I was hoping that he might be able to give us an update on what they're doing. And then if you guys want, I could twist Mr. Yates' arm to give us an update on the Winterberg files. And again, he had me moving boxes in the heat. So Jared, are you there? Well, let me see. So what, why don't I do this, guys? Why don't I show you really quick? I'll just walk you through kind of the albums that I got really quick. Okay. And so this is my Flickr gallery. I will copy this and put it in chat. We got this while we were in Reno as well. This is Matt Miller, who has a new type of air conditioning system. It's not propulsion, but this is kind of my bulk photo gallery. So we were at the house of Dr. Friedwardt Winterberg. This is, I had never heard of him before Jarod found him, but he is one of the heavyweights of fusion research. He was good friends and colleagues with Edward Teller. He won the Hermann Oberth Award. He was best friends with Hermann Oberth, who did tons of work on UFOs. This is a photo that he took of Paul Dirac. So, I mean, this guy was heavy duty. These are NASA scientists. And as you could see, there's Jarod scanning and scanning and scanning. We had Jarod scanned over like 2,000 documents. He is still going through those. So I did help him set those up. I'm teasing. Jarod did actually the lion's share of the work. And what I tried to do while we were there was also just get some photos of kind of some of the various things that we saw. So if you guys haven't seen this photo gallery, it's just, I tried to capture some of the stuff that was there. Here's a letter between Winterberg and Werner von Braun. Then, yeah, a couple of, so that photo that Jarod's pointing at there is, that is Winterberg, his spouse, I believe, or ex-spouse, and then you can't see it. That's Edward Teller in the foreground. So this fellow was amazing. The other thing was, so these file folders here that you see in this photo, he had over 100 of these, and each one of these was absolutely filled with correspondence. His daughter was there. She let us go through everything, and we tried to be very careful and focus on important things. He had, photos of himself. That is a bust. He originally came from, I believe, a very wealthy, potentially royal German family. And so he had a lot of that. That is his daughter, Astrid. She is absolutely wonderful, and she helped us with things. The other thing, some of this just caught my eye. This is like the days before the internet. So these are postcards that people started sending him. Winterberg came to the US from Germany, I believe, in 1957. He was at the very end of Operation Paperclip. He was a paperclip scientist, and he specialized in nuclear physics with a focus on fusion. And so when they brought him over, he started doing publications in the 50s and 60s, and scientists would send him postcards asking for more of his files, right? And so you could see this pile here. This isn't everything. There were actually probably almost twice as many as these. I found another box of them from all over the world, including, and I got these separately, he was getting postcards from the middle of the Soviet Union about fusion research, like at the height of the Cold War. And I was just like, that is amazing. So he had so much materials. These are the boxes that we scanned, and there were actually more boxes than this, but these are the ones that we scanned. And yeah, I mean, there were about 35 in total. And this is towards the end of the week. You can see Jarod's just about knocked out there. The photo with Edward Teller, and then just some close-ups. I wasn't able to get everything. I just tried to kind of get little bits and pieces here and there. The majority of Winterberg's career was spent at the Desert Research Institute. And so we dropped by DRI and got some photos. He also taught at the University of Nevada, Las Vegas, I believe, or University of Nevada, Reno. And so we weren't able to drop by there, but we did get some photos from DRI. And DRI is part of the university system down there, and it has some amazing views too. So that's that. And then I'm also going to take you over to the Alt Propulsion channel. And again, we got, so this video here, if you haven't seen it yet, Jarod basically ran through everything that we had found at the time. And so this has kind of the best overview. This one here it's a little bit less concise, but it has different info. So I put it up. We put this up while that's actually in his office when we were scanning. And then again, Matt Miller with the unique, the Nativus Power AC technology. So, excuse me. That's what I have. That's been the last couple of weeks.
And Tim, I can go a little more into the Winterberg stuff if you want.
Yeah. Let me spotlight you if you can. Again, everybody, please, pay attention to Jarod. He has been digging and digging and digging. He's already finding amazing nuggets of information.
Yep. So Friedwardt Winterberg, Tim already went over some of this, but I'm just going to cover it again. So Friedwardt Winterberg, he was 15 at the end of World War II. His doctoral advisor was Heisenberg. Heisenberg was also the doctoral advisor of Ed Teller and a couple other famous scientists. So that made him kind of a somebody. In the mid-50s, very shortly thereafter him getting his doctorate, he came up with an idea on how to test relativity, which is what led to GPS. So that was one of the things he made sure everybody always knew him for, was that he helped invent GPS. He, in 1959, from 55 to 59, he'd been working in Germany's fusion area, which deals with a lot of nuclear stuff. And that caught the attention of the US. And the US said, well, we want to make sure we nab this guy before the Russians do. So they brought him over in Project Paperclip. And Project Paperclip ended pretty soon after that. But anyways, so for 4 years, from 1959 to 1963, Winterberg was working over at this place called the Case Institute. I think he was doing some atmospheric stuff over there. He did a lot of other stuff too. He was a polymath in his area of fusion and nuclear weapons and all sorts of other stuff. So he worked there for 4 years, eventually decided that he wanted to move to the desert and high elevation and not have to worry about all the allergies associated with living in Ohio. So 1963, he moves over to Nevada, and he spent like the rest of his life there from 1963 until he passed away in October of 2022. He wrote 250 plus publications. He cited 2,500 or 3,000 times. The dude was a heavy hitter in the scientific world. Some of his papers, though, are really interesting and are what led me to him in the first place, because I've been going down this rabbit hole trying to figure out, is the government TR3B thing, is that real? If it is there any smoking gun documents that I can find that help support that this indeed was a real thing? And if so, when was it made and by who, and all that jazz? So he had some ideas, starting with something called Project Daedalus, which was this idea that you could have a deflector dish on the back of your spaceship and a string of beads of nuclear bombs ahead of you in space. And as you go past one of these, it explodes and it accelerates you. And then the next one, it accelerates you. And so you can get up to like 0.4 C with this string of beads thing. However, and that idea is what got him the Hermann Oberth Award, Hermann Oberth being another one of those Nazi rocketry space travel type guys. So that Project Daedalus thing really put him on the map for a lot of people. In 1973, slide aside, in 1973, Dr. Winterberg ended up joining CUFOS, the Center for UFO Studies, which is the organization that was started by Hynek, J. Allan Hynek. So Blue Book ended in 1969. Hynek knew that about 5% of those cases were super amazing. So in 1973, Hynek started his Invisible College. That's where you had Vallee and some other high heavy hitters in that era of ufology. Well, Dr. Winterberg was one of those board members of that very elite organization. And I just corresponded with Jacques Vallee a couple days ago. I was like, hey, I just saw your name come up with Winterberg. And he's like, oh yeah. So this alternative propulsion thing is something that Winterberg has been with his whole life since like age 10. He was all about alternative propulsion and how to get it done. He thought fusion was the answer. The cool thing about Project Daedalus, though, is that that was the version 1.0, was these nukes behind. Eventually, he figured out you can use much smaller explosions much more rapidly and on the center underside of a craft, and that's how you can end up getting really good accelerations that way. And when you look at the undersides of some UFOs and the undersides of the flying triangles, you see what looks like to be some kind of fusion reactor, some kind of pulsing plasma thing, something there. So that is kind of what led me towards thinking, well, maybe this guy's ideas contributed to the development of this flying triangle craft. I've yet to find the smoking gun. I have found a couple of warm barrels, but I haven't found the smoking gun. He kept his UFO stuff and his work stuff very separate. Like he had one box of UFO stuff, and he had his UFO notebook that he wrote all his notes in and everything. That was completely separate. He had all these bookshelves in his office, and like he had one bookshelf that was all his UFO books, and then everything else was all his work stuff. So even though those two things have tons of overlap, even though I have letters and correspondence where he's talking to Ed Teller about UFOs and how the UFOs operate, I still don't quite have that smoking gun. The best thing I got to go on right now is in his UFO notebook. He's got some notes about a phone call he had with Teller, and Teller was saying these microfusion explosions seem to be how the craft are operating. So there's some there, but you know, I'm still going through the stuff. So hopefully I should have all of his documents that we've scanned and collected. I should have those completed and ready for like sharing to the world here within the next couple days. Right now, I'm just getting everything all searchable text, right? Because it's a scan, so you got to go through and convert all that scan into searchable text. So yeah, look forward in the next couple of days. I'll make sure I share the link on like the APEC WhatsApp chat and, you know, other maybe a YouTube channel. I don't know. I'll share it all over the place. You'll get a hold of it.
Awesome. Jarod, thank you so much. Thank you so much. Yeah. I mean, again, tremendous amount of information. We got so much, and Jarod has been going through that night and day. I mean, it's just like drinking from the fire hose. He had so much. Some of the things that I saw were in those boxes. One of the challenges that we ran into was, like, as an example, Winterberg would take like an article from a magazine, or he would photocopy some pages from a textbook or a chapter from a textbook sometimes. And then he would take notes, sometimes on it, sometimes he would attach it with staples. And then, you know, one of the challenges was like, what should we scan? What should we save? Right. And, you know, keeping in mind, we had about a week to go through those. It was, again, so much information. And his notebooks were the same way, you know, with correspondence, right? I mean, there were so many letters from so many different scientists that he interacted with. It was like, what should we focus on there? So it was really interesting. And then for me, this raises this larger question of the legacy that these scientists are leaving behind, as well as members of our own community, right? I mean, unfortunately, a lot of the older people that I think we grew up with some hero worship for, they're leaving us. And that raises some big, challenging, difficult questions, right? Because like in the case of Winterberg, he had a ton of unpublished papers, things that he either never planned to publish or he never quite got it there. And it's like, I think all of us to some degree have that. How do we save that? How do we preserve that brilliance? Now, I don't really have good answers, but one thing I did hear about was Dr. Kevin Newth said that there is a professor at Rice University who is at least trying to start an archive, and I will I'll put his info in chat for you guys. So I think Eric has his hand raised, or he did. Let me see.
I just wanted to wonder if he meant fusion or fission.
Fusion. Believe it or not.
Fusion.
Well, so yeah, they were fusion research started with Philo Farnsworth, right? So way back in the day in the 50s, Philo Farnsworth, the inventor of the TV, was doing fusion stuff. And then you had these projects like NERVA and things like that, where they started out as atomic fission rockets, right? Which is what Randa was asking about earlier. And they pretty rapidly started to explore ideas for fusion propulsion. And again, Jarod could speak more to this, but there's a lot of fusion test areas at a place called Area 11, which is basically, it's kind of across the Nevada test site from Area 51. And so one of the interesting things, and again, this goes to these unanswered questions, was Winterberg used to drive down there, and he told his daughter he was going to Area 51. And we weren't sure if that was, you know, like maybe she got confused or something like that. So we followed up with her, and she said, no, Dad used to drive down there, right? He wasn't flying to Los Alamos, although we did that as well. And when he went, he'd say, you know, hey, Astrid, I'm going down to Area 51. You know, wouldn't you love to go with me? And so he did say that to her, although it looks like it's more likely that he was going to Area 11. And it could be that the majority of what he was doing was just investigating possible contamination. I guess that was a task that he took. So. Yeah, it's, you know, there's a kernel of truth in every myth, right? So Area 51 sounds better, but it looks like more likely than not it was pretty boring stuff, at least most of the time.
Yeah, just to add on to what Tim is saying, that entire Nevada test site area, we got some cool pictures of different underground fusion stuff that they were testing all over the place. So look for that, you know, when I share it as well. There's a couple of really interesting terawatt test facilities that they had going on. One other thing, so Dr. Winterberg back in the 70s came up with, because he was a polymath, he was all over the place with a bunch of great ideas. One of the great ideas he had was this thing, which is called the Planck ether. That's his version of a grand unified theory. As far as I can tell, there might be some there, but there might also be some issues there. But considering he was so well connected, considering he started the idea in like the 70s and didn't publish this book until 2002, when he'd already conferred with Robert Ford and Eric Davis and Hal Puthoff and all these other guys to like iron out the kinks of his idea. It's probably worth taking a look at that. I should have a digital copy with out equations in that repository for people to view. The reason why there's no equations is because compression errors on that digital version. You can't really find these books online. It looks like all of the remaining copies are in the shed that had all those boxes. There was like 300 copies there that he had. So Astrid was kind enough to send me off with about 15 copies of these. I've already mailed off a couple, but so if you're interested in a copy of this book, you can reach out to me. I'm right now, though, I'm only sending it to people who are like, you know, top tier physicist level, people who are already able to understand grand unified theories, right? Because I think that there's enough of a there in this book that it deserves at least a looking over by qualified individuals.
Awesome, Jared. Thank you. Thank you. So guys, let me see. It's option Y on Mac or Alt Y on Windows. Who has something they'd like to share? Again, it's open discussion, ad hoc presentations. Does anybody have updates on the research or anything along those lines? There's Drew. Drew, go for it, sir.
Hello.
Hey. Let me spotlight you, Drew.
Hi. We're getting too close to our corporate demonstration to kind of delve into the updates from my project, but I want to throw out an impossible. Today's testing, even for me, it was crazy. So I want to just toss out some really raw data and some really raw information and see if anybody can make any heads or tails out of it. And anybody that wants to collaborate, I'll be looking to take on somebody to talk about this, because it's for me, it's a rabbit hole and I can't go down it right now because we're too busy trying to, you know, get funded. But let me just throw it out there and then y'all see if there's any reality in this madness. So let me see how I'm going to do this. I am going to.
And Drew, if it's okay, do you think I could drop your email into chat?
Sure. Yeah.
Okay. Let me do that.
If I get spammed, I'm just going to delete it though.
Well, and again, I'm not going to put this.
Block it
I never put emails on the open web, and I would urge everyone else not to as well. There are literally software programs that will go out there and scrape those out of chat forums, websites, all that. But in the Zoom chat, this is not public and it doesn't get published. So
I'm
there we
not
go.
at all sure what's going on. Can y'all see anything? Can y'all see
I
a screen?
can't. It looks like you shared the entire screen and not maybe you wanted to do
maximize
that.
the image.
Yeah. That's the idea. Okay, we're going to start here because I don't know how to even present this data. It's so crazy. But I'm running a test of a multi-stack plate set, and it's a new configuration, but it's based on a configuration that should have worked fine, and it didn't. So I decided to flip the polarity and run it in reverse just because, you know, I could. And it worked fine. I started at zero thrust and applied voltage. That's what this red line is, down to around 7,500 volts. So I'm applying voltage and then cutting the voltage off, and then applying voltage and then cutting it off, just to see if the thrust would go up or down or sideways or whatever it would do. And from the outside, the test looked very normal. I would apply voltage, I would get a corresponding thrust. The fact that it's drifting down, there's no drift in the system. The system was actually running very well. So it's actually making more and more thrust as time goes by. That's because we're actually driving charge into the polymers. So it's getting closer and the local electrostatic fields are growing. But that's not what's important. What's important is that this thing made thrust. I put on power, it made thrust. And I was pumping in somewhere in the zone of around 1.8 milliwatts. That's about how much power is coming out of my high voltage power supply, passing through basically a 100 mega ohm resistor, so I don't short anything out. But the system eats about 1.82 milliwatts just to run. Not all of that's being used to produce thrust. Probably 99% of it's being used to produce heat on the 100 mega ohm resistor. I just want to let you see that the test as a whole went exactly the way all the other thousands of times I've done this test. So I'm just going to put this down here, and I'm going to run a short video. I don't know if you can hear the words. I assume you can't. But take a look at the sign on this power supply. That's in microamps. That's negative microamps. It never, when I was running this test over and over and over again, I was actually generating power. And even for me, this isn't possible. This is pure madness. This system is actually creating power enough to be recorded on the current meter of the power supply. So I'm gonna
Drew, but if you flip the polarity, wouldn't it see the current going in the opposite direction?
No. When you're charging up these plates, they charge up and they draw positive power. When you turn off the power, all the energy that was stored up in the capacitors, these things are just capacitors, all the energy that was stored up comes out as negative. So it goes in as positive and it comes out as negative, which makes sense because you're pumping power in and some of it comes back out. Now I've got to sort of stop this before we get to some other parts, but I'm gonna go over this again. So, and again, I got a better little piece of this presentation. Take a look at this current. This is for real. This is somewhere in the zone of 1.82 milliamps, or milliwatts. This is in milliwatts. This stupid thing was making milliwatts of power. And it was doing it for hours on end, which is really disconcerting because even I don't understand what's going on. Okay. That number should not be ever negative. Okay. This is the first time in 4 years of running these tests I've ever seen that power supply have a negative output or input at this point during an actual making thrust test. And this thing was making, I don't know, 330 to 500 micronewtons of thrust and power at the same time. So I'm going to close this, and I'm going to...
Drew, is this the first time you ran a multi-layered test?
Oh no, no, no. I've run many multi-layer tests. This
I
is
also
the first
noticed on your
time I've
first
run
chart.
one as compacted as it is, though.
I also noticed on your first chart there was an inversion in the second pulse. Instead of weight change, it went up. You see there the second pulse on the left?
Over here?
Yeah, over there.
That's me cutting the voltage. So here's the voltage going on, and then I had some kind of problem. I don't know, I had runaway current because this thing was real sparky. So I cut the current and let the thing recover to see what it was going to do, and then put the current back on, or put the power back on. This is voltage.
Yeah, but when you put the power back on the second time, it looks like the weight remained up. So you're saying there was a spark over or something like that?
Oh yeah, this was super
okay, that makes
sparky.
sense then. That makes
super
sense. Okay.
sparkiness. Yeah. So I'm just showing that in general, when the power's on, the thing's making thrust, and when the power's off, the system discharges and it goes back to not making thrust. But
so all the data on the left there is bad because you're dealing with sparks.
Yeah, anytime you got a spark in the system, it throws garbage all over the place. And we'll just go through this a little bit at a time. This was the highlight. This is one of the high points. It's making 0.28 microamps at 6,500 volts, which worked out to be 1.82 milliwatts. But the thing is making 1.82 milliwatts. It's not eating 1.28 milliwatts. So for hours on end, this thing went from making power to 0. And then as soon as I turned off the power, it would plunge down and dump all the energy that was in the system. Well, I don't know where it was getting the energy from, because it was outputting power the whole time. It should have been eating power the whole time. And when I ran it in reverse, or actually this is the reverse, when I ran it forward, this stupid thing actually did consume power. It was around 0.12 microamps. That's it's supposed to be. It's always supposed to be eating power. But there's something curious about this configuration, which is in this blurred out area here, that this is the first time and this is weird for me, okay, guys? And when it's weird for me, it's very weird, because I've seen some insane stuff coming out of this research. But even this one's got me, I have no idea what's going on, because even I know this thing shouldn't be generating power while it's making thrust. So
I can point you to where to look about that if you want.
Okay.
Look, Drew, if you, there is a research by Garrett Modell and from University, which one? Colorado. Okay, and he built a device with some gaps and stuff like that, and he's able to, like a chip, and he's able to draw energy from the vacuum. That's the way. Your system is full of capacitors. Even you may have, I don't exactly know, but it's a very wild guess. You may have an issue, or not issue, quote unquote. You may have a similar situation what Garrett has, when you have two gaps and basically you have some tunneling and there's a difference in energy. Then you may be getting energy from the vacuum, but just a wild guess. Okay.
Okay. Yeah, I'm kind of thinking that's what's going on. I know we interact with the vacuum. That's how because we're stealing momentum. That's where we're getting our momentum from. We're stealing it from whatever, the virtual particles or the real particles or whatever the hell's going on down there on a Planck scale. That's where we're getting our energy. That's where we're getting our momentum from. So I'm used to seeing lots of momentum stolen in the directions that I know it's supposed to happen. It's the first time I've ever seen energy come out of this experiment. I was sort of seeing this nonsense a couple of days ago, but it was real close to 0, and it was like 0.04 positive, and it would drift down to 0.04 negative. I'm like, oh man, I must have a calibration problem with my current detector. And it turned out it wasn't. I checked the current detector. The current system is working. and this ain't working. This is stealing energy from God, and that makes me worried.
No,
I don't
look,
mind
look at
stealing
his
momentum,
paper.
but I don't know about
Look at his
stealing energy.
paper. You'll see similarities in terms of gaps and stuff like that. That's what I
Did you
think.
drop it in the chat or something?
I don't know. I can send you an email. It's Garrett Modell. He's working with Hal Puthoff and stuff like that. I'll try to find it. Okay, hold on.
Thank you very
I
much.
think-
Somebody
I'll
mentioned
drop
that
in
it
the
might
chat.
be
Hold
a
on.
radio broadcast. I doubt it, because it's an all metal vacuum chamber, and the entire plate set is inside of an ITO shielded box, which means it's inside of a Gaussian shield. So there's no radio waves getting inside that box. And it would be, I would see, if it were truly a radio station and I was absorbing energy as an antenna does, then it would be working while it's off. When the power's off and it's not making any thrust at all, I'd still see the current. I'd still see, because it'd be reading the current from the antenna. But it's not doing that. When this thing is off, it discharges pretty quick. I'd say about 60 seconds, and there's no thrust, there's no current. The current goes to virtually zero, 10 to the minus 5 or 6. So that I don't think it's the antenna thing, but that's thanks for the suggestion.
I wish I knew what you were doing. Do you have a schematic of what's going on here? There are many experiments that I see, and I just don't see what's going on at all.
Yeah, well, that's the problem, is I can't let you inside unless you decide to become a collaborator. And that requires an NDA and joining our team. So, sorry.
It's just meaningless then to look at these graphs and curves. I have just no idea what you're doing.
Okay, it's meaningless to you then.
All right.
But there's a couple of guys on this team that have seen the insides of this, and it's not so meaningless to them.
Well, I'd like to make meaning out of it.
Well, so Eric, I did put Drew's email in there in chat, and in fact, let me drop that in one more time,
and we'll see what we can do.
All right.
So and let me see. I have a couple more questions, I think, for Drew. And Harry Sprain has been dropping schematics and videos into chat, so I want to go to Harry in a moment. But let me go to Michael Perrone first, sir.
Hey Tim, yeah, good stuff, Drew. I think Garrett Modell's work, it's a possibility. If there was a spark initially during the test, it could have created a conductive pathway partially through the thing that would have. You could have created some sort of diode, and then if you have that sort of situation with an asymmetric capacitor, you have asymmetric vacuum states. So it's possible you could get power out of that in some geometries.
I would really like to explore that. So can we get together?
Well, that's Garrett Modell's brainchild. So I do recommend talking to Garrett Modell for that, and I have an insight here or there about it, but definitely I do also recommend speaking to Garrett about that. But if you're, I recall you mentioned you were thinking of using iron phosphate for embedding charges, and if you are using something like iron phosphate, couldn't it just be a battery? Couldn't it be just storing charge over time?
I thought about that. This particular design has no storage. There's no storage potential in this particular chemistry patch. This particular one. I thought about that too, but it did do a little sparking early on. But by the time I was getting to these kind of readings, it had been running spark free for hours.
Well, you mentioned also that you had put it backwards and it was somehow working. So
it was working differently. It was producing thrust both directions. It was producing way more this direction than the other direction. So just by flipping the polarity on the plates, I was getting a different thrust direction and a different thrust.
That was different than the usual amount, right?
Yeah, it's less than the usual amount, but that could be because of the configuration. It was a brand new configuration, and I haven't worked the bugs out of it yet.
Maybe. One thing I was thinking is if it produced thrust the opposite way that you expected it to, maybe it already had a charge embedded in it.
No,
That
it produced thrust the correct direction that I was expecting. So it did its thrust right. It even did the quantities kind of right because I knew this wasn't going to work that well. The only thing that's out of the norm on this one is in one configuration, it burned energy just the way it was supposed to. And when I flipped the polarity on the whole system, it created energy at some ridiculous amount. It was ridiculous the amount of energy it was creating for what it should have been burning. So not only was it not burning it, it was generating it, which
yeah. So one thing that I saw is in these sorts of systems, and this is something for Garrett Medell's team to look at as well. But in these sorts of systems, when you apply your electric fields, the amounts of power output can increase drastically. I mean, you guys see the amount of thrust go to the square of the electric field, I think, right? So, I mean, in principle, if you're getting power instead of thrust out of the vacuum, well, first off, I mean, if you're getting thrust out of the vacuum or power out of the vacuum, you're probably in some sense breaking CPT symmetry or at least some symmetry. And if you're breaking that symmetry, then if you're breaking the symmetry to get energy, then you can probably also break it to get thrust. Those two things, there should be a proof about those, but I haven't given it a thought. But yeah,
energy
I think,
and momentum.
yeah, when you if you have a system that is actually, this is Drew, this is something you can test. Does the power output of this setup scale with the square of your electric field, just like the thrust does? That's something you can test. Because then that's sounding like a vacuum effect.
Yeah, and energy and momentum get combined into a 4-vector in relativity, so they're kind of related in that sense once you're in special relativity.
Thanks, David. That's good. In addition to the other, but yeah, I mean, I think the test to be done here is how does the output power scale with the applied voltage? Is it to the square or exponential or what?
I can look into that. Thank you. That's an interesting thought.
Good luck. And I would be
you.
very curious to know the result.
Yeah, so would I. So I'll get back with this one. Anybody that's interested, just email me and we'll see if we can collaborate on something. Because again, this is a rabbit hole I don't have time for, and I probably am not going to circle back to this until I get some other stuff taken care of. But there's a whole bunch of really coolness here. And I just wish I knew more about this nonsense. So that's it. All I got, Tim.
It's a lot of fun.
Oh, sorry, I was muted.
Oh,
let me go to
anybody else got any other question? Oh, yeah, there's a bunch of hands up.
let me go to HFK, who's been patiently waiting.
Drew, before you do any tinkering with the device that has the anomalous results, make damn sure that you've got all your construction notes straight and duplicate it first and work on the duplicate to see if you can repeat what you've just done. Because you might have a one-off, but if you can reproduce it, get the same test results, the same anomalies, then you know you're onto something.
Yeah, that's very sound advice. Thank you. Unfortunately, this is a anomaly that popped up during a high pressure design effort I'm under. So this is actually going to get its little butt tore apart tomorrow, and the next generation ain't going to look nothing like it. So that's why I know how to build this. I know exactly what I did to get to this point. I do have a full set of design build notes,
However,
along with videos and everything.
As you're tearing it down, multiple cameras in case something changed. When you said there was an arc over, so something may have changed.
Multiple arc overs, yeah.
Okay, so video the damn thing, take lots of photographs, because you may have some clues in the teardown that won't be obvious.
Yeah, I do forensics on every build, but since I don't know what I'm looking for and I don't have time to mess with it, if you're interested,
you just contact me. We'll get together and maybe you can propose something to do with the data, because I'm going to take some pictures and some video, like you said. But there's not going to be a lot to see because these things are just, they're just metallized polymers. So you can't really see anything. I mean, I do a quick capacitance. I do, I don't know, some of the other nonsense Charlie asked me to do. We do voltage drops and discharge versus voltage. And there's all kinds of nonsense that he asked for. None of it makes any sense to me, and I don't really care. I'm just looking to make thrust out of this thing. So anyhow, that's what I got. So next.
Thank you. Yeah, let me go to Trevor next. And Curtis, actually, after this, I want to go to Curtis. And the reason is Curtis is on a schedule. He has a family member with a birthday today, so he's stealing time from that to spend with us. Trevor, go for it, sir.
Yeah, so I don't understand your setup, and I don't need to know. But so forgive me if the question is naive. But where is this power going? Are you like pumping electricity back into your lab? Like if you see your power meter, is it running, backwards a little bit or something? Where is this power going?
Good point. Basically, these are commercial Spellman high voltage power supplies. And the high voltage power supply has a 1 giga-ohm resistor that goes from the output of the high voltage power supply back to ground. And it measures some sparky thing. It measures across that. It's in 16 bits, and it reports the voltage that it reports the current that it sees. So it's a very accurate current meter attached to the output of the high voltage supply. So if the high voltage power supply is putting current into the system, then it sees the current flowing in. If the system is backing current into the high voltage power supply, then it sees it the other direction. At least I'm not a Sparky man. I really don't understand electricity. I assume the voltage stays the same and the current just changes direction. I really don't know, but every other time I've run this thing, and I mean, I've run this thing thousands of times, I see the current always in positive. It's always a positive current that's getting burned. And when I shut off the system, the energy that's stored in the capacitors comes back out of the capacitors as negative current. So I see, I've seen lots of negative current, but it's always after I hit the button and turn the thing off, and the current always goes into like negative 0.1, 0.2, 0.3, 0.5, and then dumps it. Yeah, you get that for 15, 20, 30 seconds, and then goes right back to zero, and no more thrust, no more nothing. Everything's copacetic. This is the first time I've ever seen negative current during 6500 volt output.
So you're saying essentially it's just going to ground and you're just reading it as it goes to ground.
Yeah, it's going to ground and I'm reading it. Yeah.
I think it would be interesting to have it not go to ground, see if you could charge a battery with it. Or something.
And
I mean, that would be interesting because it could be a instrumentation error.
But right now it's just an anomaly in the output. So I don't know what to do with it.
Yeah, I would just want to kind of see it, to know that it wasn't like an instrument failure.
Awesome. Well,
No,
Trevor,
I don't believe it was an instrument failure. I don't know how to turn this thing off.
Yeah. Oh, Drew, so I stopped sharing, and actually, if
thanks.
it's okay, let me go to Curtis for an update. I asked Curtis because Curtis had an update he was going to do at the last APEC, and we didn't have time. So, Curtis, could you do an update for us?
Sure thing. Let me.
Thank you, sir.
I'll share my screen and.
Yeah, and again, for everybody, I visited Jim and Curtis about probably 3 weeks ago, a month ago now, and the work that they're doing is absolutely amazing. And I think the thing that impressed me most is how much upward potential there is as well. I didn't realize, they are pursuing things one step at a time very rigorously, but Curtis ran me through a bunch of the things that could be done to improve thrust over time, and it just blew me away. You're talking hundreds, potentially thousands of times more thrust. So that's amazing.
Yeah. Well, it is a physics lab, Tim. So, so thank you. I appreciate the compliment. So first thing, let's see, can I? There we go. So this is a picture of the new device, and Jim calls it he calls it big ears. And I basically the difference if you look at dig up an old picture of the previous devices or pictures of the other devices we have. The bearings we have are simple sleeve bearings. This is one with that's a self-centering bearing, and I'll talk about it more later. But this is one of the improvements that we're doing. So here it's pictured just with a aluminum slug in the middle. It doesn't have a stack. This is when it was being constructed and just fit for fitment. So, but that's what it looks like, and it's set up so that you could have bearings on 6 ears, although initially we ran it with 4. So this is the kind of the big signal we got, and I'll show in the next slide a kind of rough guesstimate of the force that we're generating. And what you're looking at here, and I'll show, and after I show that slide, I'll show a video of this run. But what you're looking at here is the blue trace is the calculated average momentum of the device and the structure holding it, which is the torsion pendulum. The device itself is noted in green. And of course, this graph is Michelle ran this on Tracker. This is a great software, great contribution by Michelle. We really appreciate all her efforts. She's going through some health things, so she had a whole thing prepared. She was going to present to Tim, and so we're still waiting on that to happen. I want to make a note of that and acknowledge her work. So the green is the device itself. The blue is the kind of the averaged momentum, and the red is the torsion arm. So it's a lot more massive than the device. The device is about 150, 160 so milligrams, and the device is more like 800 milligrams. So almost like in total, it's about about a kilogram of mass. So anyway, so what you'll notice is that when the green motion happens, that green graph like moves quite a bit, and the blue doesn't move that much. Those are we're expecting that those are stick slip type events where you're not really, you're exchanging momentum. Maybe the thing's vibrating and walking or doing some crazy motion as it vibrates. Now, what you're looking at in this graph from 0 to 40 seconds is there was a sweep. You can see at the top, it was started at 45 kilohertz, and it ended at 40 kilohertz. Now, again, this was a run done August 1st, so it's been a while. And usually during that time with our other bearings, you get a lot more noise. And you'll notice here that the graph, I think it almost doesn't move until it gets closer to the resonance point. And then after that, it kind of stabilizes again. So really this setup is, we're using bearings that are like engineered, and we're kind of taking small steps. We're taking steps toward getting something where, hopefully all the noise is greatly reduced. I mean, you can't ever get rid of all of it, but we're trying. Now, if it was just stick slip and that kind of motions, we would expect, the blue curve might wiggle a bit because of the energy being put in. But the fact that it, between 21, 20 and 22 seconds, that it goes up significantly. And you can see after around 22 seconds, somewhere in there, basically that minimum right before 22 seconds, a little bit after 21 seconds, the red trace, which is the torsion arm, and the green trace are both moving. The red trace stops its motion from opposite direction of the green, and then starts going in the same direction, and that continues on for a bit there. So and again, as this is happening, we're sweeping through these frequencies. Okay, so 0 is 45 and 40 seconds is 25. So at 20 seconds, that was around 35 kilohertz. So this is less than, a little bit less than that. So as this is sweeping through the resonance, you see the mass like move quite a bit. This is one of the biggest signals we've ever had. And so I was excited 2 weeks ago to try to get this. I was coming back from the lab, and APEC unfortunately ended. I was delivering a device to Jim, and so I wasn't able to get back in time. But so let me go to the next slide, and this is the basically you can see this is a graph that actually Michelle did, and you know we are. She had other numbers in there, and I want to leave that for her. And also we're validating those numbers, but you know, just from a simple physics, you know, dp/dt for force, you can just put a line through this, and you can see, given on the left, the momentum numbers, and these are, of course, like I said, they're from Tracker, and they're basically, I think Michelle was running it through ChatGPT with Wolfram Alpha in the background, you know, helping with the math, right? Getting that. So we're validating all that. That's not 100% validated, but we're working on it. I'm looking at how Tracker calculates the velocities. So it looks like Tracker is using the central limit theorem for you know, taking the first derivative, so the velocity. So that looks to be a legitimate way. And so that, you know, these momentum numbers are just taking that times the mass, right? The mass is the number you put in. So anyway, so we're getting right here for 1 second an average force of 700 kilonewtons. Now, as we're going through this, of course, this is being swept. We're sweeping through a frequency, and you can see that red is the smooth total momentum. So you can see there's times where we sweep through, and it looks like that, you know, if you take that little, if you get a smaller time, it looks like you can get a higher slope, right? The slope is going to be basically the force. Okay, so it's possible that you know, somewhere in there could be in a smaller frequency regime that, and if we're able to target that, we might be able to repeatedly get that. That's, you know, yet to be seen. But this is very promising and exciting data that we've been wanting to share with you guys. So let me stop. I want to stop here and show the video of the run. And I think at that point, I can show other things, but I think at that point, I should probably take questions. So let me, oh, actually, I should continue to share and then just go to the video. So let me share the desktop and then switch out of, and here is, I believe that was run, that was run 5. Okay, move that. Oops.
Okay, and Curtis, it's just showing us your desktop yet.
Oh, okay, hold on a second. Okay, how about now? Can you guys see the?
Yeah, it looks like it's just showing the desktop.
Okay, let me change what it's sharing. Let's see, stop share. Share that.
There we go.
Okay. Why is it pausing?
Slide it to the right. It's off screen, it looks like.
It just doesn't like me going full screen mode. So here we go. I'll just play it. There we go. And you see that push right there. So this is the video. And you can see it's nice and stable. and that was the end of the 40 seconds right there, that little blip. What we do is we do a reverse sweep really quick. So it's it kind of marks the end of the sweep. So it's meant for data purposes. So I'll do it one more time in case you guys didn't catch it. Okay. And there it's kind of just stabilizing. All right. Let me stop the sharing. And yeah, so I think if it's okay with you, I think I should take questions, Tim. And then I can proceed with a couple other comments afterwards if there's time.
Absolutely. Curtis, well, thank you so much. Let me actually, if it's okay, let me go to HFK first because he had his hand up first.
On the frequency sweep from 21 seconds to 23 seconds, was that a fast sweep, a slow sweep? And so if you have the, is there a situation where if you're not sweeping or the rate of the sweep, do you get a different result?
Yes, there's different. Yes. So and actually Jim's on here too. He can answer some of these as well. But the sweep rate is we're basically using a function generator and telling it, okay, go from 45 to 25 kilohertz and do it over 40 seconds. So it just simply just linearly sweeps. Now,
wait, high frequency to low? You
yes.
said 45 to 25.
Yeah.
High to low.
45 to 25. Yes, high to low.
And if
it's a constant. So we currently do not have.
Does it respond to a single frequency? So you see a window where you have the response and you have that dramatic movement. Is there a frequency or a very narrow frequency where if you're just bobbling around, say 5,000 cycles, would you be seeing it deflecting consistently, or does it require it to sweep in order for something to happen?
So my answer to that would be we need more data, because some of the data, I mean, Jim has done a lot of these experiments in the past. The issue is that some of them that were done on air, in the air, that experience is not necessarily valid for the effect that we're trying to get, because in the air, you're pumping air. So we were seeing that where in air, if we stick on the frequency, hey, we get a motion and we get that thing happening over 10 seconds, we get that push, or 5 seconds or whatever it was. So we used to run pulses of 5 seconds. But now, I mean, it's taking us a while to get back to seeing, these significant motions again in a pretty decent vacuum. And so now we're looking at how to lock into those frequencies. I think your question implies, like, can we, instead of sweeping for 40 seconds and then just getting a 1 second or half a second pulse, can we lock in there for a longer time? That's the next steps. We are hoping to get a feedback circuit where we can know what that range is and have that feedback circuit reset the sweep so it starts again within that window. There are runs that we have done that are shorter, like narrowed in, but they're repeated again. They're just simply repeated. There's no tracking. If the resonance, because we expect the resonance to, as it heats up, to drift a bit. We currently don't have anything in place to track that drift. That's not in place now, but that's something we're looking at.
Let me add a different dimension to it. The sweep rate is actually important, because if you go back into the mass of the effect, it turns out that mass fluctuation on which all this depends goes as dp/dt. That is to say, how rapidly the power is changing while the sweep is going on. And the faster you sweep, the larger dp/dt is.
That implies that spikes, that by having rapid disturbances of the system encourages thrust.
Yes, Yes. Do we
Yeah, in
find
fact,
that
we're not using a sine wave. We're using a sawtooth wave to help.
it's 90% symmetry sawtooth, so that you emphasize the second harmonic, which is another thing you need for this to work. What we find is that 1 kilohertz per second seems to be about the optimum sweep rate for these types of sweeps. As Curtis said, you can chop it up and do shorter things and all that, but it becomes increasingly complicated to interpret the results that way.
Stay simple. Stay simple and get more complicated after you've got the thing mastered.
Yeah, we're going to get more complicated as time goes by, because you can't do 40-second sweeps to get one pulse that's about 2 seconds long. We've got to improve on that, but it's get the simple stuff down first and then worry about the other stuff.
Right. Okay. Thank you.
Awesome. Thank you. Let me go to House CC next. Sir?
Yeah. Actually, this is kind of more directed to James Woodward, and then on the secondary basis, it's going to be directed toward Curtis Horn. Mr. Woodward, I've watched many of your videos where you made presentations concerning the I don't know exactly what you call your drive. Maybe just call it the Woodward drive or Mach effect drive.
Mega drive.
Okay.
Mass Mach effect, gravity assist, impulse engines.
So
okay. Anyway, yes.
Yes, yeah. So I read your book. It was Springer about the bases, the theoretical, and your work and so forth like that. And I know you obtained your inspiration from the 1956 movie Forbidden Planet as a 16-year-old. That's one of my favorite movies, and I can see why that's inspiring. So to get to the point with you is I know that this has been a long-term, maybe 40-year venture on your part to produce this drive, and you made some amazing advancements in this. But I just wondered, even though you would like to refine it to the nth degree, why not try to encourage someone? I know it's difficult. I'm not unaware of the difficulties, but to actually put this into deep space and run some tests on that in deep space at your best efforts, and maybe you might learn something that you haven't seen before, and see before you no longer are with us. Hopefully you won't be soon, but to get an idea of what this will do if it's in actual vacuum in deep space, and see if this can be giving you some of what you hope to obtain as your inspiration. That's what I would like to see, because I'd like to see this advance, and I would hopefully like to see your fruition of your ideas. The other thing I like to ask, and I almost forgot it, is, like I said, I read your book, and I only have a little bit of a quibble with your concern or conception that the drive is responding due to the wiggling of masses throughout the universe, and they all converge to give the effect that you need. Putting Einstein aside, I'm more somebody who's interested in quantum mechanics. Is it possible that the effect you see is really more quantum mechanical rather than relativistic, and that maybe, like the fluctuations that were mentioned by Mr. Drew about 20, 30 minutes ago, might have some bearing, the quantum fluctuation, in what you're seeing in your drive? So those are the two concerns I've always wanted to ask you about. I admire your efforts and your tenacity in following on this, but I'd sure like to hear your thoughts about those two things, the the deep space and whether or not a revision of the basic theory might be necessary. Well, thank you. That's all I had.
Okay, quick answer. It's relativity and probably not quantum mechanics. Without relativity theory, you just simply don't get any of the mathematics to express the effect. It depends on inertia being gravitational too, which is a step beyond what general relativity says. General relativity says inertia is like gravity, but it doesn't go so far as to say it is gravity. Einstein believed that it was. I think Einstein was right, but I know a lot of people who don't think so. An in-space test of this would be a very desirable thing to do. The problem there is finding a ride and the funding to put together a space-rated package. You know, these devices can be run in a vacuum chamber or in a lab here, but to do an in-space test of the sort that you're talking about, stuff has to be hardened so that it can withstand the vibration of the ride up and things like that. And that's simply a matter of finding somebody with enough money and interest and all that to say, yeah, we'll help. And we'll go ahead and do it. It's not for want of wanting to do it. It would be really nice to do. You're right about that.
Yeah, I'm sorry to interrupt you again, but the Planetary Society worked with the at the time when we had friendly relations with the Russians. They inveigled them to put on one of their ballistic missiles a solar sail, and they were able. The solar sail itself failed even after the launch, but it was a collaboration, and that for a fairly good price, they were able to actually get a launch that was relatively cheap. I understand those issues. I'm not unaware of those. It's maybe who you know, it's not what you know that gets you the ride into space.
Yeah.
So thanks anyway.
Thank you.
I should add that that getting us, something certified is a big hurdle here. We are, of course, that was one results, and the question is, are we repeating it, right? So I have a video spooled up here for after the questions to show you what happened after, and that we're working on getting the thing to be able to repeat that level of thrust, and it is tricky because this is not an easy device to put together. It's not a device, getting the fitment together, and even like how we're mounting it. So we're actively working on that and improving that, because it looks like there's something there for us to draw out. So that is, I would say, one of the major things that we want to do is get it repeatable, and then get replication, and get that published, and go after funding. So
yeah,
did you have a question for me, by the way?
Oh, no, just that you to amplify whatever he had to say. Again, I'm aware of these things. I follow the space program quite deeply, and I know that you want to refine it down to the point. But one thing I want to emphasize and is that when you put it into an actual space environment, say you were in between Mars and Jupiter and turned it on, you might see something that you never expected. What you won't see no matter what you do here on Earth. And if you want to test this drive and take it to what it can see, where it can be, you might, what's the old expression? Don't let the perfection, stymie the good.
Right. Yeah, no, I get what you're saying, but
that's what I'm trying to. Deep space would seem to be great.
I totally understand what you're saying, but keep in mind, if we're able to actually replicate this effect, that there's much more. There's vast implications for physics. I mean, this is not okay. Yeah, we can go to Mars really quick. This is all of a sudden Einstein was right, and we need to step back and figure out, what really is going on. So it opens up. It's going to open up a lot of eyes. Change. Really, it's going to be a change in how we look at the universe. So there's implications that we can't really say. It's kind of like discovering the neutron type thing.
Yeah,
right?
well, and if I could
Understanding.
Curtis, if I could jump in, one of
ahead.
the things that yourself and Jim had talked about when I visited was this is currently producing an average of, if I remember correctly, millinewtons of force, but you have peaks of newtons of force, and you had talked about, for just as one example, the 2 millimeter thick piezos. If you guys go to 1 millimeter thick piezos, you may have a tenfold increase in thrust. Another way that you can pick up thrust, if I remember right, is you were looking at a tracking amplifier that tracks the change in piezo as they heat, right? So even here on Earth, I mean, before you send it into space, you have many-fold increases in performance that you're able to achieve.
Yeah, and you know what? That's a good segue. If you want me to go to the next steps, and I can talk about what those are, and then we can take more questions.
Please.
So let me do that. Let me go to the share. Just there we go. Share that, and I think so. And by the way, this was the previous reaction mask where we have supports on both sides of the brass reaction mass. So you can see on the right here is aluminum cap. This is an older design with the sleeve bearings. And what I'm hoping to test is actually having aluminum cap with supports so that we have a longer distance between the supports that where the bearings are. And what that does is that actually gives the bearings, there's something called a 2-to-1 rule, where you have to be within a certain distance, depending on the distance between bearings, your forces have to be on axis a certain angle. You can think of it that way. So if we spread out the bearings, that should help with the stick slip issues that we're getting. So we're kind of taking steps to test that. So we're going to be testing this device again, and then I'm hoping to get an aluminum cap with ears with supports so that we can put supports on the furthest points away, and see if that helps us out. So I took videos. So here's basically I talked about the mounting, sourcing materials. Okay, so you mentioned the disc size. So we are in talks with a manufacturer of piezo stacks and piezoelectric material, and they are going to be building stacks for us, because right now, having Jim build them or I build them, it's kind of it's a kind of like a custom-made thing. So what we're trying to do is get somebody with that has a QC and we'll do repeated steps that we can produce. So we're sending them materials, and we are sending them 2 millimeter stacks, and I believe Jim is going to be sending them 1 millimeter discs as well for them to make stacks for us. So we're hoping to get more than one sample, several samples. I'm not sure how many, so that we can test those. Like you said, in theory, we should get something an order of magnitude higher, maybe 8 times. But also that is going to depend on how we drive it, like you said. So that's the sourcing. So testing other bearings, in addition to separating the bearings, I'm looking at floating bearings and other types of bearings, hybrid bearings. Those, of course, the problem is we have very small devices, so there's a limited number or limited off-the-shelf selection out there. So Jim and I are going back and forth about this, and I'm trying to come up with something where we can reasonably build this thing, right? So the discs are 18 millimeters in diameter, and I'm looking at bearings that are 10, maybe 12 millimeters diameter. So that's pretty big in relation to that. That's a lot of mass. So it's problematic to do those. But that's one of the things we're looking at is how, you know, the mounting design, and we may have to test with these other things, but that's yet to be determined. In terms of like driving the device at resonance, if I go back to that graph, what that would mean is, like, if you look at part of this graph, like right around 22 seconds, you see how that red part slopes really high. So what that would mean is that going back and going to that slope over and over again, right? That's kind of what we're trying to do. Is like we get that impulse, we stop, we go back to the beginning of that, and now that graph may, in the sweep, in the frequency, it may drift. So we got to figure out a way to track that drift and follow it and continue to get that thrust. So that should have a duty cycle where, you know, we'll have to run it. We'll be able to run it a certain amount of time, you know, let it cool down. And that's what we're looking at is getting those improvements. So there is a lot of potential. Now, as you said, in terms of the future testing, so one of the things we're looking at is testing with a fully enclosed, basically something that floats that's fully enclosed. So having a driver where, you know, we could put it in a, you know, a small indoor pool, still water, everything floating, you know, everything enclosed, including the power source, everything, and, you know, turn it on and see if the thing moves, right? So that's something that we're considering doing, especially once we get this repeatable. If we're able to repeatably get hundreds of millinewtons on average, right, with high peak forces, then we should be able to, you know, put something in the water, maybe with multiple drives, or with the cooling system, with the power sources inside, the drivers inside, everything, and see it actually move without any propellers, right? That's what we're looking for. So I'll stop sharing there. Go back to questions.
Awesome. Yeah, thank you. Let me go to Richard next. Richard, go for it, sir.
Oh, we can.
There we go.
You're muted, Richard.
Yeah. Can you hear me now?
Yeah.
Oh, okay, good. Yeah,
Yes.
so I was going to ask you, are you prejudiced towards adding a second set of reaction masses? In other words, not electrically driven, but just a damper. It would sort of look like a pie that's cut like a pizza, and it would be hinged at the circumference. And what it would do is it would take that, you know, that high frequency that you're pushing with, it would absorb it in the return, kind of like when the device was on a table at one time and it took off really fast and then it returned to the same spot. So it's that energy coming back that needs to be absorbed. And it would be the reason it would be a second reaction is because the first reaction would cause its expansion, and then it would have a contraction when it went to go from the high energy push to the low energy push that you're using there.
Yeah. So to answer your question, the device, so the reaction mass, that length has been tuned. Basically, there were different lengths tested to optimize that length, because in that brass, right, the speed of sound is a certain velocity, and you get the energy splashing back and coming back to the stack. And so that mechanical resonance, I'll call it, is in the run we just saw, was like basically spot on with the electromagnetic resonance base. So there is a step-up transformer that is part of the driving circuit that is designed to be at that resonance frequency with the capacitance of the stack, so that you get the same frequency, basically the same resonant frequency as the mechanical resonance. And so we are looking, one of the things we're looking at is we're looking at the higher order harmonics And so what we see is that when the second and fourth order harmonics, the ones that like add, I think you're implying that when those spike up in the first and third order, the odd harmonic go down, that's where we see that force start to come out. So there's a lot of subtleties and difficulties of like, if we change anything, that's why one of the reasons this takes a long time is that even when we change the supports, right, those are little like tuning forks vibrating. So even when we change the shape of one of those, that's going to change the harmonics. So we're very cautious about making changes, or Jim is. I've tried to like change everything, but
because
there's a good reason why we want to go slow.
Yeah, because to me that thing seems like it has a lot of energy in it. It's just tapping into it. So I had a similar experience with the one that I sent you a video on. So that was a vertical acceleration, but when I put that in a or actually the horizontal, and when I put it in a vertical position, I lost a lot of, I mean, I still had my directional thrust, but I was losing because the whole system was trying to balance itself out. So what I did was I went on the cross section. So my linear force is going one way, but I'm in balance. So I added this angular 30 to 45, and I just let it bounce back and forth, and it took everything that was in the vertical position or the horizontal position, and it gave it its acceleration back, which would be like literally like space. It put position where I had that complete balance, like I was in space, right? Without being in space, right? Because they just balancing itself out. Now the weird part is my linear force, right? When I moved those to the other side, it actually went in the opposite direction. So my linear force was actually dictated by the cross-section force, which was totally blew my mind. I was like, whoa, wait a minute.
Let me ask you a quick question. So are you doing, this is the experiment you're doing in air, right? You're hanging it?
Yeah, that's what, and that would be the horizontal position, right? So and
so
that
I had a suggestion for you real quick, is that you're able to videotape your experiment, right? You're able to have a camera on it.
Yeah, I sent you a video. I don't know if you, I think you took a look at it.
So what you might want to do is if you go to if you look up Tracker, it's a physics software. It's like tracker.physlits.org. I think it was like made by MIT, but it'll actually let you take video, and you can assign points on your device and actually like look at the forces that are generated and like make graphs and stuff like that. I think that might help you in understanding what's going on with your device.
Well, what I'm saying is I was able to replicate in one set of circumstances in another, but I had to add on these extra components. So anyway, I was just trying to throw that out there, because when you're but one mass is pushing the other mass, and there, you know, when it's coming back there, you know, just keep it simple. If you have an expansion,
and you were probably like if you look at the mechanical resonance and what you were changing, it's probably had to do with that. That would be my guess. Kind of getting closer to that.
Right.
So who's the next? I see 4 hands up.
Sorry, let's go to Mikolaj next.
Okay, so I have a question to basically maybe answer to how CC, because there was a company, and there is a company that's basically has a device based on quantized inertia. I'm not sure what's the relationship in what you're doing, and then maybe there's some similarities. The way it looks to me, I'm not really know. But they sent a satellite, and which basically at the moment I think that they failed. But no, the satellite failed, not their experiment, because that that's what it is. I'm not sure if you're aware of that, or basically it's Mike McCulloch. I think this is that's his theory, but the company, I don't think it has nothing to do with them, but it's about quantized inertia. That's
the
all.
IVO. Yeah.
I've heard Jim's opinions about Mike, and Drew knows about all that. So, but yeah, this theory, like Jim says, is based on relativity.
Yeah. Well, let me go to Brendan next. Mike. Brendan, go for it, sir.
Hey guys. Yeah, I'm trying really hard to understand. And forgive me if you guys have already been over this. But just out of curiosity, pure curiosity, I've previous to all this, I glanced through Sayama's paper from the 50s. And I read Jim's book as well as I could, not up on the math. Just I would love for my own layman's mind, and maybe others that might be listening, to understand a little bit more of. So you guys are you're operating on that universal field of inertia that Sayama believed was generated from gravity in the entire universe, or something like that. Forgive me if I'm butchering it. And you, in order to do that, you're acting on that by having two masses on either end of this device that are vibrating at different frequencies. With the piezo, that's what the piezoelectric buzzers are for, right? And that is somehow generating thrust. And that's the first question. Like, seeing how those all fit together, maybe just give me that glory moment of I see the light. And the other one is, now I know Jim said this most likely has nothing to do with quantum mechanics. And no, I respect that. It's a general relativity phenomenon. You don't need to even touch on quantum. But I wondered if you're familiar with the ER equals EPR conjecture by Susskind and Maldacena, and whether or not any of this possibly has to do with that connection between micro wormholes and entanglement, potentially. And that could have anything to do with that here, if you're open to the idea of bridging the gap there, because it seems like it might be connected. No pun intended. And that's my question for now.
Yeah, can I say something on that? Can you hear me?
So Jim, do you have a?
Okay, yeah, real quick. So like if you're standing 50 feet away from someone on a cell phone and you make a sound, you could hear that echo, and the closer you get. So that's kind of something to think about there. You mean Doppler, the Doppler effect? Yeah, you have like two different signals, but you actually end up with some kind of a wave between the two phones, but you have a different wave that is echoing between them, right?
Yeah,
like you have
like
you have a direct frequency, and then you have like a longitudinal frequency. So you kind of have to just think of that for a minute, and kind of, it gives you a little bit of insight on that thought process.
Yeah, I mean, mentally I'm seeing, these days I'm seeing more and more just between all these theories. It has a lot to do with energy, information, density, or tension over space-time, and there being a differential between these two locations, and in all the different applications. That's what I'm seeing more and more. But I'd love to hear from Jim and Curtis on this.
Yeah. Well, Curtis, Jim, do you guys have any?
ER equals EPR. Any comments?
Einstein-Rosen bridges are equal to EPR, Einstein, Podolsky, and Rosen, which is entanglement, incompletion of quantum mechanics. No, ER equals EPR. That conjecture is being pursued, as far as I know, by Jacques Sarfati and some friends, Ray Chow, Nathan Enan, Um, I think that's it. On Juan Ferria's Texas space operation. Does this have anything to do with that? No, not really.
No, I think Brandon was just asking. Yeah.
I was sort of wondering if there's some possible convergence between theories here. Not that you're using that
like
theory
this,
here.
yeah, like the sound when it travels through that circle there, it's going from one point to another, so it does have a relationship, even though the ER and the, you know, there's the whole technical on that, but just to get like a physical, mental reaction, you know, there is a moment in one place that can take a place in another. You know, if you have your induction working properly, you know, induction, you
yeah,
can tap along the line of induction too as well.
So Richard, let me, if it's okay, let me go back to Jim and Curtis, because they were kind of working through this from their model.
Yeah, go ahead, Jim.
Go ahead. Yeah, no, Mach effect gravity assist thrusters are actually simpler than Einstein and Rosen bridges and entanglement, stuff like that. There's a paper by Hal Fern on cosmology and all of that, where Hal worked out Mach effects on the basis of Hoyle and Narlikard's extension of general relativity to include Wheeler-Feynman back from the future signals. Okay. Curtis actually has that paper and probably can. Curtis, can you post that to these people so they can see Hal's paper on that?
Sure. Yeah, I can
Okay.
link it to the chat later.
Yeah, the devices themselves, the brass mass is the important one. The aluminum cap is just there to keep the piezo stack from tearing itself apart. It adds preload, and it has an acoustic signature in what's going on, but it's there mainly to hold the thing together. The brass mass is the thing that the piezo stack pushes against in order to maximize the acceleration of the stack near the aluminum cap, because the larger the acceleration, the larger the effect. So it's uncomplicated. What I can say is this: I'm in the process of making the first draft of what I call a benchmark paper for this project, bringing everything theory and observation and all that up to date of about this time and where we are. And when that becomes available, well, I'm near the end of the theory section now, but there's some more to go on it. But eventually that will be out there and hopefully will be easier to absorb than the book, which I wrote a dozen years ago when I was a lot smarter and knew a lot more. You know, so you're getting the winnowed down thing in this benchmark paper, but it'll be available soon.
The picture's coming into clearer focus from the foam. I see it. Thank you for answering. I appreciate that.
Well, let me move along to HFK.
Hi, Curtis, could you say again on the resonance that you have, I'm sorry, the harmonics, the first, second, third, and fourth harmonics, what was happening again?
So why don't we go to the video, and it's much easier to see if I point it out there. Let me, actually, I was going to play for you guys the very next run that happened the following day. Can you guys see that screen?
Yeah, maximize it, please.
There we go. You guys still see
Yes,
it?
better.
Yep.
Okay. And the bottom left are the basically you see the peaks in that red. So the first harmonic is about, this video has already started, so let me start it from the beginning. And you'll see those peaks drift, and you go from 40. You see the second peak is the second harmonic, third peak is the third harmonic, fourth peak is the fourth, etc. Those are the harmonics. Now, this video, if I go back here, what if you're looking at the device as an aside to the harmonics, you'll notice that if you look at the rod here, you'll notice that bearing pops out. So that we had an issue that we had to take it out and work it. So that's why we're not, we're had to rework it. Jim glued them on, and we're trying to, and now we're having trouble aligning it. So anyway, so that's why I don't have a repetition of that previous thing. So we're still working on the problems. But yeah, this down here on the left, that shows you the different harmonics and as they drift along during a run.
And you said that the second and fourth harmonics, when those come into play, is when you were seeing maximum thrust?
Yes.
Or the first and third?
No.
The second and fourth.
First, second, and fourth.
Is the thrust making itself evident after you've been pumping energy into the system, so that when it hits these resonance, energy is somehow being dumped at those resonant frequencies?
That's a good question.
Because it sounds like, for lack of a better description, you're charging it up and you're getting to trigger points, and when the triggers happen at the harmonics, boom, it moves.
So in terms of charging it up, one thing to keep in mind with these bearings, they're basically background noise here. There we go. They are self-lubricating. So when we first put this device together, we try to move that, but remember, between the stack, the thing is vibrating very quickly. So that vibrational energy, there could be mechanical effects there, and that's what we're trying to minimize with this with the bearing design.
Right, but it seems like, because it's being, the vibrations are happening and then you're doing the frequency sweep, it almost seems like the energy is being stored in standing weight. It's being stored somehow in the vibrations are being stored, and when you hit these frequencies, the resonances, based upon the current size and geometry of the device, those become triggers to let the energy loose.
Well, that's something we could, if we did a sweep and it was outside the resonance, you wouldn't get any of these motions. So it's not like there's energy being stored and then, it would have to go away, right? Something would have to happen. So, we could do that. We could run runs outside of resonance, and we have, and nothing happens. In addition to that, one of the configurations that we have, it's called the null experiment, where we take basically two masses,
right,
and they're equal masses on either side, and we run through the same sweep, and you don't see that same, motion. You see a little bit of vibration, like I said, because of the violence of the mechanical resonance, but it's nothing like what you see. So that kind of rules out. That's basically a null test to rule out a lot of these effects that conventional effects that might explain the motion. Because if it was a magnetic effect or something else, or one like you're saying, where things are, there's a
energy being somehow stored in the system, whether it's mechanical energy, magnetic, something, but it looks like it's an energy dump that gets triggered during the resonances, and that's why you get the motion.
Yeah, I don't know if I would think of it that way, but it's possible.
No, just something to consider, because it's very interesting that it happens on the harmonics.
Well, okay, so it has to happen on the harmonics because things have to align. These are, if you look at Jim's work, these are basically transient terms. So you have to be on that, you have to be in the jerk, the higher derivatives of motion. That's why it's so hard to replicate. So it's yeah.
Because the resonant region is so narrow to make it work.
Yes.
Okay.
Yeah, that's what makes it difficult to do. Otherwise, yeah. Otherwise, it wouldn't have been 30 years, I think.
Yeah, exactly.
So
thank you.
Yeah. Also, thanks, James, for all your hard work with this device. I saw like Tim's videos, and it's really incredible how much like thought was put into this device over the years, and hopefully people carry the torch and get this thing across the finish line and put it in space, and hopefully you get to see it happen. So I guess my first question is why brass? Have you tried various other materials?
Brass is easy to machine, and it's cheap, and it's fairly dense. Is the reason why brass. It's just simplicity. All it is a slug of stuff. It also has pretty good acoustic properties. So when the PZT stack sends waves into it, the waves get reflected from the open end. They don't get absorbed in the brass that much. Okay. And the reflected waves come back and reinforce what's going on in the stack. So brass is a good material. Curtis wants to run tungsten. Tungsten is hard to machine. It's expensive. When we get to an ideal design, and maybe we'll do tungsten.
Have
Yes,
you
and
have you
thank you.
considered perhaps working with a bismuth alloy or something? It can be still relatively resonant, but denser than brass.
James, do you need discs of tungsten? What
Well,
shape would they have to be?
Regarding
So
the
in
bismuth,
terms-
I can mix up some alloys for that.
What shape would they have to be?
In terms of the reaction mass, the issue is that part of it is that it's threaded. So they have some threading in the brass, and that's kind of hard to do with these other materials. And it's also Jim's using the university machinist. So materials need to be something that are comfortable with. So
How about
those are-
tantalum? Tantalum is relatively soft and machinable, although very dense. It's a little pricey, but yeah, maybe tantalum.
Given the resources and the time and all that, we'll try anything that's you can make a decent case for.
Well,
as it is.
Yeah, and you guys have Curtis. You guys have Curtis email, right? And Jim's
Yeah,
email?
we could correspond via email about that. Anyway, the other question I had was so the second and fourth harmonics, but not the first and the third. So I was thinking, so one of the things I was thinking about this device is if there's a way to produce mechanical squeeze states of the atoms in the object, then the squeeze states, we know that they have a different, I mean, this is coming at it from a sort of a polarizable vacuum, quantum vacuum approach, but trying to connect it to relativity towards a unified theory. But if you picture that the squeezed vacuum state somehow alters the inertia of the atoms, if you sorry, not squeezed vacuum, but squeezed atom state. So squeezed in the quantum sense, not like mechanically squeezed. So if you have quantum squeezing of the matter particles, and that alters their inertia, then you would expect to see that squeezing for all of the harmonics. However, the even harmonics would always add, and the odd harmonics would cancel. So you would get a thrust in one direction, but then a thrust in the other direction over the course of the odd harmonic. But the even harmonic, if you have a quantum squeeze state over this piece of matter, and that changes its inertia, then you yeah, I mean, with the second and fourth harmonic, that would always, the force would always be in the same direction through the period.
The force is in the same, well, you can get forces in both directions, depending upon the phase of the first and second harmonics and the second and fourth harmonics.
Yes, yes, but if you have the third and if you have odd
Yeah,
harmonics,
I know.
if you have odd harmonics, it will flip flop.
I hate to be a wet blanket, but quantum vacuum that you're talking about is Al Puthoff's polarizable vacuum.
Something like it, yeah.
Yeah, it's an electromagnetic theory of inertia. And electromagnetic theories of inertia are just simply wrong because the Lorentz force is the operative force in that equation, and Lorentz force gives you different masses for the neutron and the proton when you calculate it, which means that inertia is not electromagnetic. It's gravitational, as Einstein said. Okay. The problem is that when he created general relativity, he didn't put inertia into the equation of motions explicitly. It's an implicit force in general relativity, as it is in all classical mechanics.
So, but then, well, why couldn't we, in principle, imagine a quantum vacuum which is full of gravitons instead of photons?
You can imagine anything you want. That doesn't necessarily make it real. Okay, you'd have to think of some way of showing that there's a good physical reason for believing that's the case. Okay, at this point, all we need is that when you push on something, that a force arises to act against, according to Newton's third law, an attempt to accelerate an object, give it a so-called proper acceleration. Okay? That's all you need. You don't need any quantum mechanical stuff in order to get this. Okay, you'll probably find it easier to follow in this thing that I'm writing up right now. So you want to take a look for it.
I will.
Because I'm trying to strip it down so that it's just basic essentials and stuff like that, and not get off onto too many sidetracks.
One thing I would appreciate then, if you can, for college students and bachelor's degrees, if you could mention prerequisite knowledge required to understand the material, that would be very helpful.
Are you familiar with the D'Alembert operator?
Yes.
All right. If you're familiar with the D'Alembert operator and classical wave equations and all that, you won't have any trouble with this.
All right.
Okay.
Thank you.
All right.
Here's something you can. Here's something you can.
Perfect. Thank you.
Pick up on Amazon. Yeah. A very thin book. See.
Oh yeah, that's good. That's good.
Yeah.
Thanks,
That's
Curtis.
a good starting point, I think, right, Jim?
Yeah. It's a very good book.
Thank you, guys. Let me, if it's okay, let me go to Drew really quick, and then I still have my thing on Harry Sprain stuff. I want to go to Harry right after Drew. Drew, go for it, sir.
Hey, Curtis. This is, first of all, amazing. Congratulations on seeing some high watermark testing data. This kind of reminds me a little bit of back when a few years ago, when we were only making about 12 or 15 or 20 micronewtons of thrust, no matter what we did. We would start the thing into an oscillation, kind of resonance. We would actually cycle through and pulse. It was pulse DC at the time. And we would get that thing up to where we actually saw, a huge increase. We'd go like 10, 15x the static thrust in our resonance. And that's kind of what I'm thinking that you're seeing here, is that when you hit the resonance frequency, it maybe is taking your standard thrust that you would make continuously, and it's amplifying it 10 or 15 or 20x. I just want to let you know that we saw that and we were making so little of thrust that we had to see something. So that's what we did. We actually put our static system, which is a DC static device, into a pulsed resonance and saw about a 10 or 20x increase in the thrust. It's not that we were making more thrust at the time, it's that we were seeing like a resonance amplification of it. So I just want to throw that out there just in case, you know, there's one more way that the universe can try and fool you. So just be aware of that maybe, and that might have some use to you. But other than that, man, awesome kudos on the high watermark. Man, bring it on. We need your drive.
Yeah. Yeah. And one thing I'll say is that, okay, you know, these are all positive, promising. We've had things where, you know, when I first started kind of full time with the project, which was back in 2021, right? It's almost 3 years now, almost. We were doing the experiment in air. It was on a pendulum, and I was really worried. And finally, you know, I convinced Jim, you know, talked to the team, he put baffles, and, you know, it turned out, yeah, it was just air pumping. And so that was a big setback. So it's been, you know, there's ups and downs, but the big thing here is, for me, is that, you know, I want to be able to repeat this, not only repeat this with the same device, be able to make a new device, machine it the same way, it works the same or close to it, right? The replication is something that, you know, given the fact that there has been replication attempts in the past, and, you know, things have gone wrong for one reason or another, we've been unsuccessful with that, you know, years ago, and of course smaller forces than we're seeing now, but we really, for me, at least, I'm not speaking for Jim, this is me, I want to replicate this. I want to be able to say, okay, yeah, we're getting, you know, this stack, and I can change out the masses, do a null test, it goes away. I put the you know, the reaction mass in the aluminum cap, and it comes back, right? I can send that out to Mark, and you know, he can do the same thing, replicate it, right? Whoever it is. So we're trying to get there, and like I said, for me, it's a matter of, this is a physics experiment. Yes, it gives it's propelling this propulsion, the application, but really, for me, it's about the physics. I mean, that's fundamental to what we're doing here.
Awesome. Well, Curtis, thank you so much. Thank you so much. And I know that you have a family event that you have to get to, so thank you again so much. Well, and Jim, thank you as well. So, guys, what I want to do now is, if Harry is still with us, and yep, looks like he's here. Harry, do you want to walk us through? You have been dropping amazing stuff into chat, and I've been drooling over this for the last hour. Can you walk us through some of this? Can you do some screen shares and things like that?
Yes, I can. Can everyone hear me okay?
I can.
Yes.
All right. Not too familiar with this program, so let me make sure. Let's see. Screen sharing.
Yeah, so there should be a green button at the bottom of your screen called share.
Oh, share screen. There we go. Okay.
Yeah, and you can either share the entire screen, or you can just share a window.
Gotcha.
And it depends how much stuff you have that you want to share, because.
Okay. Let me open it up here. I'll just go to my website.
Hopefully we're doing okay. It's the middle of August, and in here it's at least 85. So.
Okay. So
right on the edge of passing out.
Chrome tab. All right.
There we go. So I can see myself.
Okay, you can see yourself, right? Now you can see
go.
my screen, right?
Yes, sir. Magnet modeling.
Okay. What I've invented is a propellantless propulsion system. It uses magnets to dampen centrifugal force and dissipate that potential energy as that arm is being thrown out. How do I want to see you guys too at the same time. Can I do that?
I am not sure.
Hang on, let me, I'll just make 2 screens. Then I can talk and see you at the same time, and you can see. Okay, can you see the QDE screen?
No, actually, it's showing the other screen. It's
Okay,
showing
hang
with
on.
APEC.
Let's try to stop sharing. Let's go back to sharing. Where did it go? Excuse me, guys. I'm doing my best.
Oh, that's okay. They just did a major update to Zoom, so I'm kind of lost.
That should be it.
There we go. Yep.
Perfect. Okay, because I want to be able to see you guys as well. It's sort of weird talking to myself. Perfect. All right. So what I've invented is called SID. It stands for Centrifugal Lens Pulse Drive. I found out by building a magnet model that I call Emily about 2001. I came up with an idea of how to use a magnetic field to have a rotor on the interior follow the magnetic curve as it increased in force, and it would pull the rotor around all the way to the top, and I put an electromagnet there which creates the same pulse as the rotor magnet, allowing it to jump by. And that's Emily, stands for electromagnetically initialized lateral induction engine. And I've been able to capture magnetic field and utilize that through a generator and produce more energy than I'm using. But the problem is it's not a huge amount of energy. It's just a small amount of energy. So now I'm working on scaling it, stacking it up, 10 Emilys all stacked up and working in unison. That's what I'll be demonstrating to the world. I have one now. It's self-powered. It's been running for 6 months, but it's still under testing. So I don't want to display it to anyone yet. After inventing that, there were prototypes in my lab that I had taken the rotor assembly and I made it so I could move the magnets in and out. And I forgot to tighten it. And it's running, and the magnets, as they came around to the electromagnet, it got thrown out a little bit. And as they did, it created this little punch. It sort of drove this across the thing. And I was like, wow, that's amazing. But what can I do with it? So I just started thinking about it. And I was like, wow, that's producing a little bit of thrust. Let's go and see what we can do. So I then went and built a prototype in 2011. And I went to Professor Mitchell Walker at the Georgia Institute. And I asked him, I said, hey, I have an idea. I think I've found a way of producing propellantless propulsion. And he said, what? And I said, no, I think I really did. And he said, okay, well, go build something and come back and show me. So I went back to the drawing board, and after working iteration after iteration, I came up with a small device that showed him it was doing something unusual. And you'll see the videos that I posted. If you go back to the one where it's on the scale, it's lifting itself off the scale enough where I can see the weight. It gets lighter, but it doesn't first get heavier. I would challenge you to go stand on a scale and just lift yourself straight up without first pushing down. You can't. So then I went to the next step of testing it with a piece of paper underneath it. And yes, it would jump completely off the ground so that I could pull the paper out. Not oscillating around like a bad, crazy washing machine, but all of it coming off the ground. Still wasn't convinced. Walker said, could be this, third-party energy, blah, blah, blah. I said, okay. So I went back and I built the last iteration of it, and that's the one you see that's on the torsion balance. And then I started demonstrating the torsion balance to him, and he went, wow, there could be something here. So he gave me a series of tests that I went through over 4 years, taping the rotor up, pointing the thrust straight up, pointing it sideways, pointing it down, removing all the magnets, covering the whole thing in plastic so no wind can blow on it or anything can happen to it. And it passed. It passed every single test. And he said, oh my God. So then we took it to Georgia Tech and we tested it on the water table, and it did exactly like we thought. The outside of it is trying to move one direction as the interior turns the other. So our force was going around in a circle. And you'll see that from the 2009 report, which is 2019 report. The data analysis, you'll see the thrust vector was constantly changing. It did produce thrust, as you see, but it just went around in a circle. This is what was actually happening. So we knew we had something. So I went back to the board and I said, okay, we've got to get rid of the counter-rotative forces. So we built another one going the opposite direction. This is going to stabilize it and allow us to get a thrust in one direction. So we did just that. We went back and, hold on. We went back to Georgia Tech with our newest machine that proved that it worked. Wait, where's the uh-oh. Is it not here? Oh no, that's the same hang on guys, I'm sorry. I thought I had everything up. It was the SID, you know, the regular SID. I can show it on the magnet modeling. Yeah. So we came up with this, which is the dual rotation system, which stops the counter rotation. Now the next step was, how much thrust are we creating? What is it doing? So we put it on the water table and once again started it, and it averages out at about 710 millinewtons of thrust and uses about 17 watts of energy to run the two small motors. So then I went the next step and building an actual big prototype that I could put on the torsion balance. And that is here. Yes. So this, and now the most miraculous thing I discovered about it, and I did this like 3 weeks before I went to SpaceCom 2024. I had it in my lab and I ran it at a really high RPM speed, and I was amazed. What happens is, let me get a close up of it. So this
And
is
you might want to turn turn the YouTube volume off.
Oh,
yeah, there we go.
I'm sorry. Okay.
Oh, that's okay. It was just really loud.
Okay. Yeah. Okay. So now it's running. I'm at the SpaceCom in Orlando demonstrating it to everybody, and we'll get a good close up. Okay, there we go. Okay, so you know how SID works, that the rotor arms are thrown out and that little punch creates a thrust that moves it forward. Well, guess what? If I go really high RPM, it reverses. What I mean is the rotor arm is thrown out. It stays out, and then it hits the repulsive magnetic field so hard, like a ramp, it slams it back in. And I get what I call the horseshoe effect. It doesn't go towards the gap, it goes away from it, because the punch from the magnetic field is harder than the centrifugal force throwing it out. But if I slow the RPM speed down, it reverses. The arm is thrown out. with more force than the magnetic field, and it turns around and goes the opposite direction on the torsion balance. And it also proves propellantless propulsion because they're turning the same exact direction. I haven't done anything but change their RPM speed.
Have you accounted for any airflow in this device? Because
Oh
that's
yeah, I
essentially a
covered it
centrifugal.
completely in plastic. It was in a sealed box at Georgia Tech.
Yeah, I would suspect that the change in direction may be connected to airflow because in this version it's not covered. But I know from personal experience this device should work.
It works. We've tested it every way to Sunday. We're now teaming up with Upright. We're building a small prototype, roughly about the size of the one you see now, and we're bringing it up to the space station. They're going to hold it up in microgravity, let it go, remote control, turn it on, and it's going to fly across the space station.
Very cool. I think if you
Have
had
tried
covered
out in
this,
vacuum?
Yes. It doesn't need to be in a vacuum. That's the beauty of it. It doesn't have any outgases. It doesn't produce any heat. It doesn't do anything. You can take it and place it on the interior of the ISS, just at the right trajectory, and it would keep the ISS in orbit.
it doesn't need magnets either. That's another thing.
It does need magnets. Whoever keeps saying that is absolutely wrong, okay? We've tested it without magnets. We've tested it in the magnet modeling system, everything. It doesn't work. The magnetic field is what makes it work. It dissipates the centrifugal force. Those things you showed me are stupid because they're sitting on a floor. Anything that has some counter rotation thing to it is going to vibrate. And secondly, you're not going to have something move and stop, move and stop, move and stop. I don't mean to get angry about it, but I get really sick of people trying to compare this to something else because it's not.
Yeah. Well, Harry, hold on. Yeah, I think the mistake is what you're talking about is slipstick propulsion, which is what the non-magnetic devices use.
All of them are exactly the same. They have to be on a surface. If you lift them off the ground on a pendulum balance, they just go back and forth and back and forth. They don't do anything.
Yeah,
put them on a torsion balance like mine, they don't do anything.
Yeah, that's the slipstick. And that's one of the things from the time that I spent with Jim Woodward, that's one of the things that they have been very careful to rule out on theirs. But what you're talking about is a much larger scale, you know. So yeah, I can see where you're yeah. Well, if it's okay,
Tim, no, just to reiterate that what Azrael and Israel did, his device only had 2 reaction masses, and there was 2 devices next to each other. So the pulsing that you're seeing is because the motors didn't spin up together. Had they spun up together like they did in a previous test, you'd see it runs a lot more smoother across the floor.
Show it to me on a torsion balance, show it to me on a pendulum, and I'll believe it. Again, it's on the floor. Nothing on the floor produces thrust. It's all just pushing off the floor.
Yeah,
nothing.
So Harry, have you considered? You mentioned doing it on a water board. One of the things. So one of the things that was interesting, and this again goes to the slipstick thing. Roy Thornton, you did a canoe. Have you thought about replicating the famous canoe experiment?
No, I don't need to. We're way beyond that. We've got a magnet model that produces it. I just paid $30,000 for a magnet model to be done that produces how much thrust. We're now just determining what size we're going to build. The producing thrust side is gone, guys. We did it. Now we're going to the next step.
Yeah. Well, if it's okay, let me go to Mikolaj. He has his hand raised.
So you mentioned that you say that because of magnets, you convert centrifugal force into thrust. That's what it is.
Correct.
So here is what I sort of
here it is right here. This is it, right? Showing how the magnetic field holds it back. It holds it in equilibrium between the centrifugal force trying to throw it back out. And now on the other side of the magnet, if you go to the blue side, the stator magnet, it doesn't feel that same thrust. The field is sort of dissipating that centrifugal thrust as it comes around. And only when the magnet's thrown out at the 6 o'clock position does it feel a light punch. It happens 32 times per second, 17 times each rotor, and it produces a continuous thrust.
I'll take a closer look. Basically, what I'm sort of looking at it. Have you considered that you may be, in a way, sort of pushing against quantum foam because of
that? I have no idea. I don't know if it's the ether. I don't know what it is. The only thing I go back to is what Tesla said. You can attach your machines to the wheel workings of nature, and you can have infinite energy. It also has to work in reverse, where if I'm dissipating an energy, it is continuous.
So, but because I'm at when things are moving, you are creating a magnetic field that it's basically pushing against. You say you have two magnets and positive, south or north touching each other. But if these two magnets have different strength, then I basically have a little paper about that. Then you would see if the ether exists or there's quantum virtual particles, you can push against it because of the momentum on because of the how these basically magnetic fields react with basically positive and negative. When so let's say a quantum foam consists of particles, they're popping up just in pairs, and if the magnetic field has a same polarity, okay, but different strength, and then you see some of these particles, positive would be deflected one way or the other, and the strength of deflection would be different. Then, and that could create a thrust. Okay, so this is sort of my idea, and I can see a similar thing in your case, but I'm not sure. It's just a wild guess. Okay, so that's my 2 cents.
I am fascinated to know how and why it works, but you're talking about trying to understand a magnetic field. That is the goal of everything. Everyone's trying to do the same thing to get to that super high energy state.
Look,
of whatever a magnetic field is.
And if I could, if I could interject, I think, Harry, based on where you're at, it seems like you're following a really amazing experimental path, and it's probably a bit premature to try and attach that to any kind of speculative theories,
Yeah, it's doing what it's doing. I don't know exactly why it's doing what it's doing, but it does it. And again, I'm just showing all the tests that I went through. These are all years of iterations after building it and going over and over again like this. Okay, it's spinning. Oh, is it the air that's turning it? Well, the next experiment, I turn the thrust straight up and it doesn't move at all.
But I have I'm not talking about theory. You see, I'm very skeptical of what I just told you, but I have an experiment that basically proves it. That's my point. So you may have a very similar effect, your device. That's what I'm saying. I can send you basically a short presentation.
Yes, please.
Yeah.
Okay,
Harry, maybe you could drop your
maybe
you could drop your email in the chat.
Thank
Yeah,
you.
and the only reason that I try and differentiate between those is, anytime you have an experiment that produces results, the more amazing, the better, right? People always get they get rushed by folks trying to attach a theory to it, and I think that can confuse things, and in this case, it's probably a little bit premature. So,
here's a video of it with the rotor arms taped in, running at the same RPM speed, everything exactly the same. I have the streamers hanging around it to show there's no wind blowing on it. It doesn't do anything. It just sits there.
No, so I attached the link to the presentation. You may actually see that we may be talking a very similar thing in terms of why things work for you.
Awesome. Okay,
so I've
well,
tested it every way to Sunday. I can't think of any other way to test it. And like I said, we're sort of beyond that. They're ready to build the prototype and bring it up there to the ISS and bring it to the world. This is my first introduction to the world. I've been working on this for decades.
Yeah, this is really exciting. Let me go to Jarod Yates.
Harry, I gotta say, even though I am not normally a fan of gyroscopic thrusters, even though they have been proven to work, it's a personal thing. I'm not usually a big fan. I gotta say, I'm sold on your thing. I love it, man. It's awesome. Well done. Great job. You have put in a buttload of effort into this. It's very obvious that you have worked really hard on this. So I got 3 questions and 1 comment suggestion.
Yes.
So I think you just answered the first one. So on those white rotors, you got those red magnets, right? And those move inward and outward as it goes through its rotation, right?
Correct. 20 millimeters.
Okay, yeah, that's what the second part of that question was percentage of the gap distance that's closed when it's fully close to it. Is it like 20% closer? Is it 50% closer? How much?
Yes. This is what happens. And in the video, the magnet modeling showed us this. As the rotor arm comes around, centrifugal force throws it out. It moves out 20 millimeters and it stays out there for approximately a millisecond. It is imparting all of its energy within that millisecond. And then it travels a little bit, hits the magnetic field, and is pushed back in, but not slammed in. It takes it about halfway. So there is no counterpunch to it, just one direction. And then it holds it in that state all the way around to throw it out again. So the magnet never gets the opposite reaction.
That sawtooth wave asymmetric damping it's the secret sauce. It's the thing, and like most alternative propulsion things that you got to get.
The problem was at the end there. You see that weird curve. It was getting that magnet to break away, the rotor magnet to get away from it without being captured and pulled back.
So my next question is, do the magnets on each of those rotors, I assume then they need to be in phase with each other. You can't just spin these things by themselves. They have to be locked together.
No, they can spin at any RPM because the thrust coming out is sort of like this, but it averages like, almost a straight line. So you can get, even if they're off, the RPM speed's not perfect on both of them, it doesn't matter. It still just drives along. And our recent tests that we did is we'll run one rotor at a higher RPM speed and the other one at a lower RPM speed, and I can drive it like a tank.
Interesting. Third question. So that opening that you have, it's got an interesting little rollout on it and it has a certain width to it. Can you describe the iterative process that you had to go through to arrive at that opening and that one-sided being rolled out?
Yeah, that's the key. That's the secret sauce right there. Is that took a long time to develop. As the rotor arm comes around, it wants to leave the orbit, but if you don't have that perfect little lip on it in order to bend that magnetic field around, the back of the magnet will reach around and grab the rotor magnet, slam it on the brakes. So I had to experiment and find the perfect little curve to allow it to break away. And then once I had that, I had to time the gap with whatever my RPM speed was and how hard my rotor arm comes out. And if you go to my website and look at my old pictures, you can see I've built like 14 iterations of this device, all different configurations. The rotor was up here, the rotor was in the thing. And then I got a really cool 3D printer, and then it got pretty wicked. I could build the parts I needed and things I needed. And it's been awesome. This is my life. This is what I do.
And the last thing I got is a suggestion or two. So yes. I know my experiments with my stuff that when you have a magnet and you slap it with a high voltage pulse, you get a temporary increase in the magnetic field strength. So if you wanted to have at certain points in the rotation, if you wanted to be able to time that with high voltage pulses, you'll get stronger magnetic fields, which I assume correlates to more.
Right. We're also putting in a Hallbach array, which will put a lot more force on one side, because then we could increase the centrifugal force speed, and we get bigger punch for a smaller package.
So the high voltage gives you more, and then if you need to cancel the field in certain places, you may have already looked at this. You can get magnetic shielding material, and the cool thing about magnetic shielding material is that when you put this is mu metal. When you put a high frequency signal on a mu metal, you can cancel or dampen its magnetic thing. So you can end up having like a magnetic switch by using this. So if you combine those two of high voltage pulses with high frequency pulses, you could end up getting much more oomph for your buck.
What we've got from NASA, what they've told us is it has to be sealed. It can't have any magnetic coming out of it, no direction whatsoever. I want to be able to take it and put it on a steel thing and it's going to fall off. So we're doing that. Whole thing's going to be a mu metal. And I'm thinking of putting a low voltage through the mu metal to absolutely cancel out the magnetic field.
Awesome. Awesome work, man. Keep it up.
Okay.
Awesome.
Oh,
Thank you.
Sorry. One last question. So you said you're taking it up to space. What's the timeline on that?
We're working with UpRev. We're now raising the finances for it. We got to raise $2 million, and we've got a bunch of billionaires that are looking at it and stuff. And after we raise the money, we're going to UpRev, and UpRev will build the prototype. And then we're meeting with Florida Space and all the big people and everything, and figuring out how to approach NASA or whoever. And my idea is this. I know those astronauts are trapped in space right now. I might be able to help. And the reason is UpRev could build this prototype that's producing at least a Newton or more of thrust. They could send that up, and it would be a twofold situation that's paying for itself. What that means is you now have a thruster that you could mount on the interior of the ISS at the right coordinate or whatever, in order to keep it in the right, in orbit. I don't know all that orbit stuff. And they wouldn't have to do it again by refueling it and doing all the other stuff and the orbit correction. So that would save them a huge amount of money, $60 million or so, because of the launch. So we're talking $120 million savings. That might be enough of an incentive to go get them now. And I was thinking of getting publicity behind it and everything. I think we can push this.
Yeah, awesome. Well, let me go to Zoltan next. Zoltan, go for it. And here, you know what?
I have two questions basically. Maybe I don't know if I can recall it correctly. You mentioned something about water surface. Can you elaborate what the purpose of the water surface is? And the other one is when you showed the last format to the folks at Georgia Tech, what did they say? Or is it out of their hand now? You are going to NASA instead of Georgia Tech, or are you still working with the Georgia Tech guys, or is it it grew way bigger than that? Thanks.
No, we put it on the water table in order to prove that it was producing thrust. So we took SID and we put it on the water table with a flotation device underneath it. SID was completely sealed in a frame, so no air could mess with it, no whatever. And it was put in another room at the Daniel Guggenheim Aerospace School in Atlanta. And we stood in the other room and remotely turned it on and measured the amount of thrust and how much movement it made on its own. And that was the proving point that, wow, we really did it. And then we went further and we did torsion balance test and this test and that test and everything. And then I've now demonstrated it at Spacecom, and it's just going crazy. We've discovered it. Now let's see how big we can make it. What can we do with it? What kind of things can it be used for? all kinds of stuff. It's just going to sort of change the whole paradigm of space travel, because now you no longer have to refuel satellites. You simply charge through photovoltaic cells, charge batteries, and now the satellites can stay in orbit almost indefinitely. They have the ability to go anywhere they want to go with no limitations. What is this that someone said, sorry, but not human spaceflight qualified? Are you talking about Sid?
That wasn't me.
Yeah, Gary wrote that in chat. Yeah, he worked at NASA. What he means, it's not qualified for human spaceflight, right? There would be
That's exactly what UpRev is going to do. They have all the certifications and all the other stuff. They work with Rogue Aerospace to build satellites and put them in orbit right now. So all that's taken care of.
Yeah. So let me go to Mark next. Mark, go for it, sir.
Okay, so sorry, Harry. I didn't mean to upset you before, but this is stuff that we're already working on. We've already built a device like yours. We already know that works, and we have different theories as to why it works. So
then why haven't you built one and put it in space?
Okay, well, this is one of dozens of projects that we're working on, but we have a different theory as to why it works. First, I want to ask you a couple of questions. The magnets, there's 4 magnets that are rotating around and they're sliding in and out. Is that correct?
Correct.
And they slide out at a specific spot in your profile. The spot in the profile where they slide out, that's the vector of thrust, right?
Right. And you can change that by taking the whole stator array and just turning it. We have one where we can turn it and control
the stator array, the opening of the stator array is the vector of your thrust. What you are working on is called an asymmetric centrifugal device. This is a category of propellantless propulsion things. It has nothing to do with magnets. Your magnets are a cool way of getting rid of your friction on the edges.
Show me a torsion balance test of a device that you built and have it go around in circles like mine. I
mean, Jeremiah has one like that. He can set it up on a torsion balance. We were just happy enough seeing that it works. But I'll show you in a moment what the next thing we're going to do is. 1 second. Here it is. Screen share. So this right here is our Mercury vortex engine. So this is doing the same thing that your device is doing, but it's using rotating Mercury.
Again, do you have a built prototype doing it?
We're going to have a built prototype within a month.
We're going to have
all the parts.
We're going to have. You don't have it.
No, I don't have this
theory. You have nothing.
Okay,
I have a working prototype that you can test today, right now. Theories are great, guy. Theories are great.
Yes. Theories are great, but working prototypes are a lot better. What you're seeing here is actually the Mercury that's going to be rotating around. So there's a pinch point on one side where it will spin faster than on the other side. And what that does is increases the speed of the Mercury rotating around on this side. The vector of thrust will be in this configuration will be downward. This configuration, it will be upward or to the right, and so on and so forth. Of course, the Mercury is going to be covered in plastic, and then in order to get it to spin, we have rotating magnets. Well, what's stopping it from you mean the entire device torquing?
Yeah, you have one outside going one direction, one if you turn that, it's going to start spinning.
Yes, exactly. We have the same problem that you have. We have to build 2 of these and have them counter rotating. Yes, we have the exact same problem. Basically this in the center here is a motor, and then there's plastic, then there's a little bit of moon metal that's to shape the magnetic fields so that they induce eddy currents in the Mercury and spin it around as fast as possible. So this is our upcoming device. We already have the Mercury, the plastic, the iron. We have all the materials here. It should be ready probably sometime in October, I would expect. And we have a machine shop here that we work on this as well. But the other device, this paper that I showed you before, it basically shows you the overall concept. If you look on the left, the you see how the weight, the masses, the centrifugal mass that's being thrown around is moving in and out. And the distance, the throw distance, these are big lead balls. They don't use magnets. They're lead balls on rollers. The distance that it's being thrown out is probably a lot more than 20 millimeters. It looks like it's more like 3 inches or so. And with this device, it created so much thrust that it was being thrown around in all different directions until he got it all synced up. Like you mentioned, you were correct about that. When you only have 2 masses rotating around, the device is not as stable when you have 4 masses. So, but the problem, the reason why he ended up going with just 2 masses is his motor, which was his limiting factor, was not strong enough to rotate 4 masses and overcome the friction from the rollers. But essentially, all he's doing is rotating masses around so that it rotates faster on one side and slower on the other. In your case, your actual moving mass that creates any thrust is the magnet itself. I would suspect if you change the weight of the magnet, all things staying the same, assuming that your coefficient of friction against the magnet's repulsion is able to maintain it and keep the same movement in place, you would see more thrust. But you probably need a high-speed camera to see actually what it's doing every time you make a change to such a setup.
We've already done that. We've already done that with the high-speed camera. And yes, adjusting the weight of the rotor magnets helps determine the thrust. That's what we're doing now, actually, is we're determining what size magnets we need on the rotor in order to create the thrust that's needed.
Yeah, the heavier the rotor magnets are, the stronger your thrust will be, the longer the magnet be able to fly out.
To a point. If they're too heavy, then they never
go back in.
Field doesn't push them right. So there's a equilibrium that we have to find, and that's basically what I've been working on. That's
if you were to put like mu metal on the outside of your ring magnets, that will force more magnetic field inward, so you'd have a stronger push and be able to increase the weight of your magnet. But then again, you don't need magnets.
Before, we're also doing the Halbach array, and that puts more magnetic field on one side than the other. So we're doing everything we can to increase that magnetic field, and that means we can go at a higher RPM and create more torque with a smaller device.
Yeah, but you'd want, if you could put iron on the outside of the torus magnets, on the outside magnets, that will force the magnetic field on the inside to be a bit stronger, and you'd or permalloy, or 80-20, Iconol, all that stuff. I just purchased a bunch of it. David Chester actually did, who's here, he's a physicist. He did some math on this and came up with the mathematical reason why this will work, but it works. I know it works.
Well, thank you, Mark. Well, let me go to HFK really quick. HFK, go for it, sir. Henry? Oh.
You're on mute.
No, I'm not. I've been doing it from the laptop with a microphone on off, so I'm surprised it got flipped. Okay, so looking at the patent application, I see that the body, that the magnets are all facing north. So are the rotating magnets, are those south facing or north facing? And are they free floating, so to speak?
Yes, they're in repulsive state, neutral. The north are facing each other.
Okay,
so they're repelling.
So you're doing north.
Or south.
Well, yeah. So, but the secret sauce is it has to be in repulsion, and this kind of has a vague similarity to the Kawhi magnetic motor.
Actually, I invented another one called Emily, called electromagnetically initialized lateral induction, and the Kawhi motor was as one of the samples on mine, and I received my patent over the Kawhi motor. The Kawhi motor uses repulsion to pull it around to the electromagnet, and that has no ability to create torque. As soon as
Right.
you add any kind of torque to it, it just stops. So I took that and reversed it and used an Archimedean spiral in the attractive state. So now my force is increasing. So now I'm able to capture that rotational energy, put it through a generator, and light a light bulb.
Okay. And are there any springs on the rotating magnets so that when you get to a certain point, you're forcing them to be pulled back in?
Well, it's not forcing them. It's the opposing magnetic field that slowly pushes the rotor arm back in, but it doesn't slam it in. So you don't get a counter-reactive force. You just get a punch in one direction. And that's also why all these other devices where they actually hit something and stay on it all the way around don't work, because that force is equal in all directions. Nothing has changed in the whole.
This one you're smearing the force.
Right. When you're doing something to dampen it, read the paper I posted on the two magnetic springs. That gave me the idea that you are repelling energy. And then on my Audi, the TT, the front is electromagnetic suspensions. It reads the road in front of it and adjusts the amount of electricity to the shocks.
Right, the rheostatic fluid.
Magnetic field, exactly.
Yeah.
And I don't know what this Searle effect thing is. I've seen this many, many times. This guy was a nutcase, okay? He didn't do anything. I've read everything he's done. Nothing's ever come from it. All you have is this weird device that spins around and makes a ball spin around, but I've never seen it attached to a generator. I've never seen it produce electricity. I've never seen anyone do
Harry,
that.
I'm gonna just hold you up right there. So since you're new, you probably don't know, but on this forum, we try our best to support each other, not really attack. We'll ask questions and but you know, especially when you're talking about stuff that other people have worked on for decades, right? And maybe you've like read up on some stuff, right? We try to be as inclusive as we can here. Just heads up.
Okay. All right. Okay. I just like results. If you're going to say something about something, show it to me. Don't show me a magnet model or whatever. I want to see a prototype. I want to see it move and do something.
And
I think Harry, we love that attitude, and hopefully by October I'll have a prototype for you.
Wonderful, awesome, dude. If you need help, let me know. You know.
No. I actually, if
the whole case is, we all want to get this thing to space. We all want to prove the same thing, right?
I have a question, Harry, and this is less like I don't have anything in mind asking this, but so it rotates around and you have the magnets lining it, right? That go around the lining. Have you ever considered making those electromagnets so that you could switch them on and off? I don't know what that would do, but it seems like that might be a next step.
We did, and it doesn't really do anything. We've looked at it. It's more complicated than.
So it added complexity, but not enough thrust.
Yeah, it just there's no.
Harry, here's the reaction matter. Harry, here's the mercury that we're going to use for it. Yeah, I have like 2.5 times this amount, but that's what we're going to use in the first thruster.
They just found that in Mexico. They just found in that temple that there's thousands of gallons of mercury under it.
Yes, that's what I'm trying to explain to you. The best way to build this device is with spinning mercury vortex engine.
We'll argue on that. What was Al Tesla? What's the other one? Edison.
Actually, Tesla and Edison both came from New Jersey, right here.
Where would they get thousands? See, this is why I feel like the slow kid. Where would you get thousands of gallons?
This opens up a whole door, man. You have to make mercury. It's not natural. So why did these people thousands of years ago or whatever making a huge amount of mercury, which is poisonous?
Where would you get it? Where would you?
I have mercury vortex engine. It came out of a spaceship.
Because it crashed.
Yes.
On your current device, what is the how much thrust do you get out per joule of energy?
17 watts produces 710 millinewtons of thrust.
Wow. So gang up a few of those and you've got a a nice chunk of thrust.
You got it. That's exactly what we're doing. We're determining how much thrust per level, like we'll stack them or, whatever.
Well, a fun project, if you could churn out a reasonable number of them, even if it's powered from the ground, you got a cable going to a test frame, power up the rotors, and just say, hey, here it is, power in, levitation out, because you've got the thrust up. And never mind about trying to optimize it so it can fly by itself. Screw that. Have a big ass power cable to it as a demonstrator. It's like, okay, if this doesn't work, why is it working?
But what we're finding is that the energy to weight ratio, I've run it through some AIs and through some other things. It's telling me that I can build it where it creates enough thrust to lift itself off the ground. That's my next, that's what I've been working on.
A turbocharged Chevy 350 as you're running a generator?
No, it actually doesn't have to be that big at all. The RPM speed is the key. 255 RPM is all you need. That produces almost a Newton of thrust. Now we look at the weight of it. How light can we make it? And that's what I'm working on now. I'm looking at Goralite. I'm looking at other materials that are as light as possible. And once I have those numbers of actually what it will weigh and the amount of thrust that I can create, I'll have a computer model of if it will be able to lift off the ground.
Well, and if I could offer, let me offer a suggestion really quick. One way, this is kind of a cheat, right? But one way that you might be able to do one hell of a demo is if you use like a lighter than air to offset it to neutral buoyancy. And then it should, in theory, at least at a certain altitude, right? It'll just hang there and you can use the engine to move it up, down, left, right, whatever you want.
Now, I was thinking about that. There's that guy on here that puts those big balloons up all the time. And he's always putting them up there and blowing up or whatever. I think we might contact him and do just that. We want to put one on and turn the thrust in one direction and have a wind vane hold it in that direction. And then watch it. Does it actually push itself along or do whatever? And then release another one with nothing on it and measure the two.
JP Aerospace?
Yes, I think that's it. Yeah.
Yeah, airship to orbit.
Big, giant airships.
Yeah, airship to orbit. The different model of getting up into space slow.
Yeah, he does it for schools and eggs. He's sending eggs up there and food and all kinds of stuff. So I don't think it would be a problem.
And Harry, just one thing real fast. Where do you get your magnets from?
Dexter Magnets.
So I'm not familiar with Dexter Magnets, but I know this. K&J Magnetics.
They built a $100,000 magnet for me. That magnet that you see me standing on is 1,000 pounds. It cost $100,000. I had to have a $25,000 cage built for it. And that's my secret. You guys can't see that one yet.
Okay, well, K&J, for the really small ones, I don't know how powerful they are, but K&J makes these half-inch.
They're 54 grade. So what's that? That's 3.9 Tesla at the core. So at the face, they're like 4,800 Gauss, somewhere around there. They can hold about 80 pounds. 1 inch by 1 inch by half an inch.
What about the small ones on the rotor on the outside? How big are those?
Same size.
Same size.
Now I'm having Dexter Magnet build one solid array instead of individual little magnets. It's just going to be one, and we can just punch them out.
Oh,
do
wow.
They do? You know, my interest in magnets was more about composition, right? Because neodymium is what people use now mostly, but I have been reading what Michael Perron knows about this. Iron nitride, I think that's an up and coming.
There's a new one they found that supposedly has a better outside electronic ring than the neodymium. The neodymium has one electron that's missing, so that creates the punch. Supposedly this one has 5, but I'll have to research it more. But if it is true, then following what's happening with the neodymium, it should be an extremely strong magnet. I want to get my hands on some of it.
It might be interesting to inquire with Dexter and see. I read an article just a couple of weeks ago about that, and
We're
it sounds...
meeting with them next week. I just got back from Cape Canaveral, meeting with UpRev, and I just got back to Key West. In fact, last night. I'm a little tired.
No, I'm right there with you. The only reason I mention it is, from what I read, the manufacturing for those is very spotty still, right? It's under development, and some folks are kind of doing it, and other folks are kind of not, and it's hit or miss. But it'd be interesting
So I'm
to see.
going to wait until it gets a little more traction, a little more proven, before we start looking at any type of initiation into what we're doing.
Is that Dexter Magnets in Elk Grove, Illinois?
Yes.
Okay.
Yeah, they built, for the past decades, they built many, many things for me.
Yeah, Harry, this is super exciting. Thank you so much for sharing this for us.
I am a quiet inventor. I don't, I just invent and do it. And then once I have it, I put it out there. I don't sort of bait people along with, oh, it's going to come. We're going to have this, and I like to get it done and then show it to people.
How dare you not make vaporware?
Well,
vaporware, is that what it's called?
Yeah, vaporware. That's where something is promised, and that's all ever it is. It's a promise. It's vapors in the wind.
That's horrific.
It's a diverse. I would say we have a very diverse community, and the APEC conference, we've pulled from. I mean, for instance, you have a lot of theory people, right? Like we pulled from folks who were at the STAFE conference and Glenn Robertson and the SPCIF conference. So you have a lot of people who are mostly involved with theory, doing few experiments. And then, we have a lot of experimental builders, right? Who are very light on theory, but heavy on experiments. And so it's kind of a mishmash. And that's one of the reasons that I try, and like Jarod mentioned it, we try and preach tolerance, because we have a lot of people who are just coming at it from different angles. And, it's unfortunately, a lot of it's just not always speaking the same language,
Agreed.
And also the other problem is transient phenomena, stuff that you see happening, but the bloody thing won't repeat itself because you've got some kind of stupidly subtle conditions going on, and sometimes you hit it and sometimes you don't.
Well, that was the problem I read about that EM drive. Their whole testing method was suspect. They had nothing clear and defined to show any type of thrust without it being some Iranian, it's the power cable, or it's this, or too many variables, nothing just simple. Put it on a torsion balance, cover it up so no wind can blow on it, put it in a sealed vacuum. If it moves, wow, you've got something. If it doesn't, then you have nothing.
Yeah. Well, let me see. Does anybody else have any questions? Does anyone else have anything they'd like to present? Again, Harry, I'm so appreciative. Thank you so much.
Jeremiah.
Come on,
Jeremiah.
Where's Jeremiah at?
Jeremiah built one of those.
So Jeremiah was talking about the
guys. I invented this in 2001. That's when I came up with the idea.
Jeremiah was talking about. I did see him post about the jerk reaction, and so one of the things that I was interested in was there was a fellow named Jeffimenko. He was talking about electrical arcs, but his idea for the jerk reaction, this goes way back when, right? And he was talking about when you have an electrical arc, that jerk that happens when it is non-conserved, right? And which, Harry, that sounds very similar to what you're describing. And so when Jeremiah pasted that in there, it would be interesting. I don't know if Jeremiah is still here or not.
Yeah, I'm right over here.
Yeah. Were you talking about the Jeffimenko thing?
I've been studying these drives. They go back quite a number of years. Trying to think what the earliest iteration of one of these types of
the Vimanas.
Oh, okay. If you want to go there, then yeah, that would be the earliest iteration.
What's that? 4,000 or 5,000 years.
Thing that flies.
Yes,
I think
it
the
works on the
earliest
same principle.
iteration. I think it was around the 1950s that you get the first versions of this starting to come out. But this is a really simple one. I mean, I built a bunch of different versions of this thing and played around with it, and we've had a bunch of people on this conference, the Alternative Propulsion Engineering Conference, that have also built various different iterations of this, and with varying degrees of success and forces, but pretty much across the board, they all work. So this is a little one that is about as cheap as it can get. I mean, it uses friggin' Amazon magnets, which are notoriously bad for quality because they're not checked like K&J Magnetics or any of the good quality stuff. But inside here, there's a set of 4 little individual sliding magnets that are inside of tubes, and so there's a magnet that can go, to one side of the tube and the other, and then the magnet array that's on the inside of the back steel washers act as the vacuum plate to force the fields really and concentrate them between the 2 pole sides of the system. And so as this rotates around, it'll push those magnets back and forth along the axes. Now, here's the interesting thing about this.
Take it right now in your hand, put a string in it from the top, hook up your power to it, and hold it up in front of us and turn it on. Will it pull to one side and stay?
Yeah, it does. I've actually got some power here. Let's see. Just hook up the alligator biscuit. I don't have a string that I can hang it from right now. Unfortunately, that's a rig I have to set up. But
no, I mean, find a string behind you, a wire, anything, and put it in the center.
Can't you just hold it from the?
Hold it up in front of you.
But anyways, I'm not really here to have to prove it to anybody because I've already done the test and I've already got the videos of it. But it works on a pretty simple principle. And to just kind of explain it, if you can see this diagram,
take a wire behind you, man, and show it to us.
Just hold on. I'm not going to go set up a demo right now on the spot just for you. Sorry, but
all right then. Okay, it's great talking with you, man. I don't know what else you can share.
It's okay. We're just sharing ideas here. I mean, that the whole purpose of the conference is to share ideas about this.
That's great, but there's wires behind you. It's so simple. You can put 2 wires on it, hold it up right here in front of us, turn it on. I just saw it running. Put it on the table. Let me see what it does.
Not going to get into it with anybody here. Anyways, if you just hold on a second, I can finish explaining the principle. So on one side of the rotation, as the magnets are rotating around, they are stationary, fixed in their position. They don't change distance from the center of the rotor at any point. They stay the same exact distance. But on one side of the rotation, as they're moving around, they're wobbling back and forth. So they're taking that kind of motion, and as you can see, there's this zigzag motion on one side, and on the other side there's nothing. And so technically there's a tangential relativistic force, centrifugal Lorentz transform. We end up getting an orthogonal or tangential reaction, transformation of the electromagnetic field vectors that are interacting with stator magnets that are on the 2 pole pieces on either side, and with the rotor magnets that are moving back and forth on the slides. And so this is a really pathetically small force that this thing generates. It's not like what you have on your demos where it just kicks right up and it gets going. It's a very, very small force on a torsion balance, but it still gets going. And other versions of this have worked better, and other versions have simply not worked at all. This is very RPM specific because it has to do with...
I'm sorry, this is great, but I'm not going to believe you until I see a torsion balance or a pendulum.
I'm not here... I mean, no offense, but
I'm not offending anyone, but I mean, isn't that the point of this? To get over the BS and
I'm here to talk about ideas.
What works and what doesn't work?
I think what one thing that's interesting about Harry's is so like with Jeremiah's device, I could hear a lot of clicking, and with Harry's, I would bet that those magnets really help. So, in terms of centrifugal devices, right? This goes back to like, I think my first exposure to this genre, this idea was James Bootstrap Cox, right? And the problem that Bootstrap had was these things would shake themselves to bits within minutes. Yep. He would turn it on and the mechanical just, yeah. And so one of the things that I like about your design is partly the way that you've designed the magnets, and partly because it's using a magnetic field to push it back in instead of using a mechanical armature. I was just thinking about it, and I'm like, I would bet you that that's a hell of a lot smoother than trying to grab that weight and suck it back in, you know?
Yep. Minimal vibration inherently.
Yeah.
Exactly.
The reason that we did these different iterations with different axes of orientation, checking for the effects, is we wanted to see if it was a relativistic effect, an electromagnetic field density effect, or a moving magnetic field effect. And so you have epsilon and mu that you can modify in the refractive index, your two main gauge factors that are easily modifiable. And then you've got your relativistic forces and your Lorentz transformations. That depends on relative velocity of an observer, like the framework, for example, of that encasement. That's the observer. It's a stationary frame, as is the outside. But the rotor, on the other hand, is a motional part. So it has a different relativistic velocity, and therefore it has a different relativistic momentum along a certain vector axis as those parts are moving. So, I mean, if you're saying that GR doesn't work at all in this context, and that's completely outside the ballpark, then that's fine. That's your opinion. I'm not saying that GR is complete. It certainly is not. But even as something as simple and incomplete as GR, this is already there. So it's a principle that's been around.
Well, so you're saying that this is supported by relativity then?
Yeah, it is. It actually fits into the framework, but you do have to apply some electrodynamics systems and use other frameworks in the pieces where it's not completely flushed out. And folks like David are really the experts on it. David Chesker is fully capable of computing those numbers.
Yeah, I actually, you're kind of blowing my mind just by saying that. That kind of opens up a whole, this is kind of like what Curtis said, right?
Well, this is why we're going towards liquid mercury vortex engine kind of stuff, because it's a straightforward system. There are no parts that are slashing back and forth. There's no sudden jerk motion or anything like that. It's going to be finally the first test that we have looking purely for the tangential force transformation. And it'll be a very, very smooth operating system, virtually silent if the VLDC makes, depending on what we use to drive it.
Now, out of curiosity, Jeremiah, in terms of the mercury aspect of this, just because it's hard to work with and toxic and all that stuff, is there any way to come up with, I'm just wondering, like some kind of an ionic fluid, right? Or is that just not?
Very much so. Very much so. I mean, you can pass current through it. Bussard has a system that he was using, I think, Galenstan on, and it's a much safer replacement to mercury. Still has the same problems of amalgamation on various metals, so you have to get these really expensive metals and prime surfaces so that you can pass high current through it. But using magnetic induction to simply rotate the system instead of having to pass current through it is a much less complicated situation, because you can use plastics now for your enclosure. High-strength plastics like G10 or other materials that are suitable for the process, and can actually take the kind of pressures that are exerted out on the sidewalls as the acceleration and deceleration forces from the liquid mercury mass is changing.
Yeah, that was what I was wondering about. And I'd wondered if you might even be able. Yeah, sorry, Drew. Sorry, go for it.
I'm just curious. Okay, and all this electromagnetic stuff and spinny stuff drives me crazy too. But
yeah, I hate the mechanical side of it too. I
you know, I'm not saying none of this works, but I personally don't think any of it's real. But if it is real, are you saying are you converting the momentum of the electromagnetic field into linear momentum? Is that what you're effectively doing? Or I forgot, does yours have magnets or fields in it, or is this a purely mechanical thing?
Well, okay, to answer your question about the mercury version that we'll be testing out soon, it does have magnets in it, but the purpose of the magnets there is not to induce any kind of electrical potentials beyond the point of just simply accelerating the mercury fluid. So the idea is that it's a non-contact way to get the mercury flowing with a reasonably high torque and velocity without having to use electrodes and have any other metallic compounds in contact with the mercury that might cause it to amalgam.
Okay, so when you get all done, you got it spun up and you're in a stasis situation. It's a purely mechanical system at that point, is what you're saying?
As this
So
first,
you're
and then we would like to see if we can adapt to a purely electromagnetic driven system where it uses field coils to produce the same rotating magnetic field and
Okay, so-
the same task.
at some point you're getting the energy.
Inertial propulsion. It's
Right, so at
taking
some point-
inertia. It's taking inertia in an asymmetric form and converting it into a vector of propulsion.
Okay, so you're basically
Asymmetric
taking
centrifugal force.
rotary inertia, rotational inertia, and somehow magic, love it. You're converting rotational energy, rotational momentum into linear momentum. Is that what you're? Is that
I mean,
that
yeah.
David, do you agree with that?
If we skip like the 3 steps that need to be there in between, then yes.
Okay, yeah.
makes my
I mean,
brain
however you
hurt.
get the thing spun up,
Between two
once you got it spun up.
A rotating device, and we are turning that into a linear force.
Okay, now just out of curiosity, while you're going this way, are you slowing down because you're stealing momentum that would keep it spinning? If in a perfect universe, it's all spinny, it stays spinning forever. All of a sudden, you're extracting momentum out of it and you're converting it to forward propulsion. So are you slowing the spinny thing down? At some point, you'll be accelerated and the thing will stop spinning because you've used up all the energy?
Hey, Drew, have you ever put like a fluid through a pipe and then had the pipe change radius? So it's like Bernoulli effect. So if you have something with a velocity and the area decreases, then the velocity increases.
Yeah.
And
we just saw a great example of that the other day.
No, logically, the fluid will slow down as you get linear thrust. So that means you still have to pump energy back in to keep the fluid,
let's say
whether
you
it's
don't pump
mercury or
energy
whatever.
back in. Let's say you don't put it back in. I just want to see where it's going here. So you're taking the mechanical energy of the spin and you're converting it to linear propulsion. At some point, the energy's coming from somewhere. Are you stealing it from the
Right.
universe or are you stealing it from the spinny thing?
The spinny thing. It has to be from the spinny thing.
Okay, so you have a purely mechanical system that once you spun it up like a battery, now you have like a flywheel, you've got energy stored in a spin. You've then got some clever way of converting it to purely mechanical thrust or purely momentum vectored thrust. Am I hearing that right?
So far as what I've been able to test, friction is so high in these systems. I mean, we're talking many orders of magnitude higher than the noise floor that I could possibly detect to see whether or not it's actually stealing energy from the rotation. And that's one of the reasons why we want to move to a smoother operating system.
It sounds to me like I forgot I don't see his picture up there anymore, but the guy with the asymmetrical magni spinny thing.
Harry Sprain.
Yeah,
guy
it
with
looks
the
like he's just
asymmetrical thing.
Hi, hello. Dude, I'm an aerospace mechanical engineer. Anything that spins, and
Drew,
got wires
you're
attached to it. Like magic.
I was going to say we've made it
theory of how Sid works. It's all right there, guys.
But he did not use the word spinny thing anywhere in it.
That's okay. So it looks to me like the spinny thing you did, dude, is you're putting energy in so that you can maintain the rotation, and then continuously extract that rotational momentum into vector, right?
Right, that's the idea.
Yeah, that's
honestly, I think what
into lateral force.
Honestly, Harry, I think what Jeremiah said might be true. Awesome. There's so much friction in the system, you can't really know whether the energy you're putting in is to overcome friction or is it actually converting it to linear force.
In his system,
I'm 17 watts, and I'm getting out 710 millinewtons.
Yeah, I'm going to take him on.
I know, but you might be putting in 0 watts when friction is accounted for.
But hold on.
If you account for friction in your system, if you account for all the friction in your system, you might be putting in 0 watts. How much you're putting in 17 watts total? How much of that energy is going towards friction?
So are you saying it's over unity then?
All that's turning is the motor. I'm just turning the motor. There's no other friction. Nothing touches anything. Our magnet
But well,
model,
the magnets slide in and out. They have friction.
oh, a very minute amount as they come in and out. Nothing to disrupt the system.
That counts. That's friction.
So I think, Mark, I think what you're insinuating is that once you take friction into account, he might be approaching unity or over unity.
I don't know about unity or over. But Drew is working with asymmetric capacitors, looking at forces that may be, there may be zero energy being put into them because he's able to charge up a capacitor and see it move for hours with no. Yes,
well,
you have a way to actually measure that, but with a friction device like what we're dealing with, just to keep the motor running takes a certain number of watts, Harry. You can run that test. See how many watts. Then there's the air friction. There's a lot of things going in there. It might be zero.
I think that might go to Harry's other device, right? Harry, you said it's been running for several months.
Yeah, that's Emily.
So
yeah, I mean, and you did
that's kind of cool.
It's self-running, right? When you said it's running for 7 months, that means it's powering itself. You don't have to provide it with external power anymore. Is that
correct?
Basically?
It's all running off the magnetic field.
Right. So,
okay. So that means you're stealing energy from the universe.
Here's a small one.
Because you've got loss.
What happened?
Well, you've got loss, so that means you're stealing energy from somewhere. That's very cool.
Oh yeah.
I mean, that means you're actually stealing energy from the the Planck scale nonsense that this all.
Look at the video I just posted. This is Emily under load. It is powering a small light to show that it is under load. I used a axial flux alternator as my generator system. The energy going into it, I published the paper on it. It's a pulse width of about 36 milliseconds at about 12 volts at about 3 amps. And the output power, the Newton force, is almost 2 Newton meters and 10 radians. So my output force is greater than what I'm putting into the electromagnet if you count the pulses. But if you just put the actual number, 12 volts at 3 amps, it's not enough. But I've found by stacking them and firing electromagnets in sequence within 1,000 milliseconds, I can greatly create my torque to have a self-sustaining machine.
Yeah.
And firing 5 electromagnets or 10 electromagnets within the same 1,000 millisecond or 1 second period requires the same amount of energy. It doesn't matter.
In other
words,
that video of Emily, and I just watched your video that you posted of Emily, and man, that is a beautifully, really powerful build. I'm just looking at the amount of forces that are involved there, and that's
the magnets are horrific, man. We had to build contraptions to put them together. Hundreds of pounds of force. I almost broke my finger a couple of times. Yeah, we have some incredible stuff that I'm slowly bringing forward. All my publicity people are working. I've got my company formed now, everything, and it's all bringing forward. This isn't my first invention. My first invention is a non-toxic insecticide called EcoSmart. I saw dead ants in a sugar bowl, and why did they die? So I went to the library and researched all about chemicals and how calcium carbonates and all these other things. And I came up with a powder formula that could kill insects. I took it to the flea market and started marketing it as hazard-free, all-natural pest control. At that time, I was working for a limo company, and the lawyer of the limo company, his name's Steve Bissett. He saw what I was doing, and he's like, an insecticide? What is this? Blah, 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 blah. Long story short, patent search on it, no prior art, raised some money, got Dr. Isan Inam from Baker Donaldson and a bunch of other people from Caltech and all these working on the entomology side of it. And we discovered a new compound called hexahydroxyl. So we took that and we raised $35 million through Goldman Sachs and Lehman Brothers, and it's nationwide. It's now the #1 selling insecticide on Walmart, through Walmart. It's and Amazon. It's EcoSmart All Natural Pest Control. And the guy that I founded it with, Steve Bissett, he's now the president of the company. So I made money and I moved on to, research and development, which I love, which started the whole magnet motor thing. And I invented the insecticide in 1997. And so that was my first.
I just watched your video, and your spinning thing is that just, you don't have any batteries hooked to that thing? It's just, you just feed it back into itself and it stays spinning for 6 months?
No, that is SID, and there's small batteries. If you look right before the voltage converter, for the motor controller, there's 2 small batteries taped to the torsion balance. No, SID is not self-powering. There's 2 different devices. SID is a propulsion system. Emily is a powering system.
Okay, I'm looking at this.
Why
thing
don't
says
I do
Emily.
a live demo? I did a live demo at SpaceCom 2024.
He's actually one of my team was actually at that and looking at it.
Yes.
And he was stunned. He's like, dude, what is this thing? And then I had no idea I'd never heard of it. So one of our guys actually
he's talking about the Emily one. So that one, so with Emily in that video, I think that's the one he's talking about, where you feed
but I'm
that
looking
back
at this
into itself.
Emily.mp4. Is that the spinning thing that goes forever?
I'm sorry, what?
Oh, he's asking if Emily is the one that runs continuously.
Yes, that's the Emily stands for electromagnetically initialized lateral induction engine. Emily.
So basically that thing is going to stay spinning for 6 months, making a little tiny bit of light, stealing energy from the universe.
Correct.
That's a unicorn, man. That's
what?
That is the holy grail.
Oh, but there's a lot of ways of doing it. Look at these. I figured out how to do it many times. Look at this one. You're gonna like this. It's called Square Emily, or Super Emily. And now I'm building that.
What? Yeah. Oh, okay. I see it.
Harry, do you have a Philosopher's Stone too, like that could convert everything into gold?
I don't know what that is.
Oh, he's just joking. I think.
And this is double the torque. I figured out how to double the torque on Emily. Have it one ring on the outside and one ring on the inside. One electromagnet firing both.
Harry, I got one other question for you, if I could.
Sure.
You were talking about how it's going to be a little while before you get up into space. You were also talking about a 10 stack of the spinny things.
Yeah, of Emily.
Yeah. So
the spinny thing is an official term now.
I'm making sure this sticks. So if you have this 10 stack of them, you said you were making about 700 millinewtons of force. So a 10 stack, I assume will get you.
No. Emily produces electricity, no thrust.
Okay, I'm asking, is it possible that you could create a 5 Newton or greater version of thrust of your device?
Yes. Oh, yes. We could possibly produce 50 newtons.
But my question is geared towards is if you had to put pedal to metal and put 100% of your focus into getting to the 5 Newton threshold, what would the timeline on that look like?
We're working on it now.
The reason I ask is because I've heard that some of the big boys really care about like that number.
Minimum to get.
Oh yeah, that's the key. You guys have to understand. This is where they are. This is directly from Mitchell Walker, the head guy at NASA. He does all the Hall thrusters and all that stuff. Man, he just got $11 million to try to increase their thrust, and he can't do it. Their benchmark is 54 millinewtons for 1,000 watts. That's the best they can do.
Harry, if I could ask, and I should mention that, so we've got about 15 minutes left until we close things down for this session. This has been mind-blowing. I'm going to have to look at this. Harry, I did want to ask, I may get myself in trouble. Have you thought about using Emily to power Sid?
Very good. Absolutely wonderful, Tim. That is exactly the idea.
I saw, I was like, wait a minute, this one's electricity.
And actually all in one system. Picture an Emily that is a Sid.
I'm seeing like the infinity symbol in my mind.
That's exactly is it. Isn't that wild? It really is the infinity symbol.
I'm just seeing the characters of Ice Age, Emily and Sid.
That that's right. That little bucktooth thing that was chasing the eggcorn. His name's Sid.
I would have never made that connection, Mark.
No, I was thinking of that movie. It's a virtual reality movie when the really bad guy was called Sid. They took all
Emily's
the personalities
the elephant.
Crazy. Remember that movie?
Emily's the elephant there, or the woolly mammoth girl, and Sid is the sloth.
There's also a Sid in a virtual reality movie where they like download all these psychopathic tendencies or something into this guy, and he's called Sid, C-I-D, and it's standing for something.
Yeah, that was Denzel Washington, and
I remember that one.
That's it. That's it.
So Harry, I didn't quite get an answer on that. So what's the really rough time frame looking like on when you break the 5 Newton mark?
We're working on it now. That's actually one of our goals, is to produce about that much, because we found from NASA that's their number. If you can produce 5 newtons of continuous thrust, you have done everything they need.
So you think like a month, a year, 5 years?
If one
you put a
produces
lot of
5
faith in
newtons, we'll
NASA.
just stack them.
I've been down the NASA path. It doesn't go anywhere. It's a 10-year black hole. You're far better off with one of the big aerospace billionaires.
Yeah, we got that. We're going directly to Elon Musk, and we've got we're talking to, what's the lady that she's the vice president of SpaceX?
Gwen Shotwell.
Weeks. Yeah, I'm supposed to meet her in a couple of weeks.
I go rescue those astronauts stuck on the space station.
That's what I'm trying to do. I'm going to offer them the ability to not just go up there and rescue the astronauts. They'll be able to use SID as a propulsion system inside the ISS to keep it in orbit. So now they don't have to come back and refuel
to get something on the ISS legally.
Excuse me?
Years. It takes about 10 years to get something approved.
That
to
is
put on the space
absolutely,
station.
I'm sorry, but that is absolutely wrong. Absolutely wrong. We've already talked to the people that get the permits and all the other stuff. It's not as hard as you think to get a scientific experiment.
It is exactly as hard as I think.
Okay.
We have a bunch of NASA on our team.
Well, I've got huge money behind me, and let me tell you, we can move mountains.
Well,
Harry, sorry, go ahead,
Good luck, man.
I was just thinking that the stranded astronauts thing might be a motivational tool for NASA.
That's the whole point. It's not just that, it's the publicity of it, this and that, who's going to be first? Blue Origin?
The only way that you're going to be able to get your device to do that is to get Boeing involved, because they're the ones who are going to save all the egg on their face, because what's looking like is going to happen is they're going to come back on a SpaceX capsule.
We are already in the works of speaking with a lot of people about all that. I don't handle that side of it. I'm the scientist. I've got a whole board of directors, and let me tell you, I've got a board of directors.
Another group that you might consider is all of the satellite manufacturers, which expands your customer base. So you have Raytheon and Boeing and Lockheed, right? They get a lot of DoD contracts, but then you also have non-US based customers as well.
Agreed. And what we're looking to do is we want to prove the technology and then just license it out and have it available to everyone.
Yeah, I was thinking AFRL. AFRL is interested in stuff like that. Yeah, and then there's also the Defense Innovation Unit, but Harry, I think that you're beyond them already. I think they're for earlier stage ventures.
Mm-hmm.
But yeah, well, again, absolutely amazing. So we have about 10 minutes left. Guys, I should ask, does anybody else have anything that we should squeeze into this one? I mean, again, we've had some
I could
amazing...
give a quick update on the Altaphon setup.
Yeah.
Oh, you're the guy. You're the guy with the lab. I saw you. I know who you are now.
Yeah, Mark
yeah,
has an amazing lab.
I do a lot more than just rotating mercury and magnets. This is
Yeah,
dynamic
yeah,
nuclear
yeah. That's a power
polarization.
thing. Yeah, that was cool. Yeah.
This is not power. We're trying to make matter weightless over here in this machine. And basically it's being tested in a vacuum with a magnetic field RF coming in from the side.
Very
and we're
cool.
using the combination of the magnetic field and the RF to orient subatomic particle spins, make matter weightless through nuclear spin orientation. So this is our new setup I picked up from Hathaway. And while setting it up originally, the glass tube where the sample is supposed to sit broke. And turns out that the size of glass tube that we need is not manufactured in the US. It's made in Europe, and the company does not ship to the US, but we found some company that sells ants that had it, and they were willing to send it to us. So we got it in just the other day, and we're at 7.4 to the -6 torr right now. But one thing I found that's kind of interesting, Drew, I want you to have a look at this. I'm getting a funny signal. This is from a force sensor inside here, and it is in correlation with the RPM of the turbo. I got another pair of probes set up over here. That's the peak signal over there as well. So basically, you're getting an RF ping that's coming off the turbo that's ending up inside of my signal, and it's also bouncing around inside all of the ground. So that's something we gotta figure out. That's one of the next things that we'll be working on. And I already showed you guys the mercury vortex engine thingy that we're going to be working on in the near future. Great having Harry on. That fit in well. We also got a new microscope, and I've been staring at the Arts Parts UFO piece. I had it hooked up here all week, and we're just staring at it. This is a metallurgical microscope, so it has the light coming in through the objective,
right?
Which is pretty cool, and it's good for looking at opaque things like the Arts Part sample, which is a piece of one of those UFO crashes.
Yeah, cool. Very cool.
Yeah, well, so Mark, do you have any photos from that? Speaking of which, I would love to see photos.
I have them on this laptop over here. I need to figure out how to transfer them over. Also, I didn't get as much time as I would like. There's this microscope has so many different filters. It has like 6 different filter combinations, separate filters that you can then combine with different setups.
I should send you a sliver of my necklace. It's from a meteorite, the one that crashed in Siberia, and let you look at it and see what it looks like. I should slice a piece off the back.
You know what?
Oh yeah, sure. That would be cool.
You know, Mark, actually, I was also thinking, remember earlier we were talking about looking at Drew's, and Drew, you were saying you probably wouldn't be able to see anything with the anomalous thruster. What if you had that under the metallurgical microscope? Maybe you could identify something that way.
No,
I mean,
it's a good idea, but no, I've got access to a scanning electron microscope too. But the stuff that makes our stuff work is macro. It's not down on the atomic level. But
well, this is not on the atomic level. This is macro scale. One more thing that we got that was working over these past few weeks is asymmetric Casimir cavities. It's basically a Casimir cavity that has I'm going to show you this with my hand. Let's say it was sort of like a ramping shape, like that would repeat itself over and over again. Let me see if I can show this out for you. Basically, if you were looking at it edge on, it would look kind of like this. It would slope down and then and move along. And the metallic surface was only over here. The vertical part wasn't metallized. And when you put the 2 plates together, it would create a vector moving in some direction. The guy who came up with this idea, Robert DePius, I asked him to come on tonight. He couldn't make it, but he lives locally, and he came to the lab to have us to help him manufacture it, because you need to have a way to only metallize half of the ramping surface of the for the Casimir cavity. It was like 1 inch square. The ramping surface that I'm talking about is microns. It's extremely small. What he actually used was a Fresnel lens.
That's because I remember you talking about those earlier in the week.
Yeah.
Yeah.
Charlie was talking about that. There's a whole that's the whole bug wing thing, where the bug wings convert microwaves into propulsion. And that is one deep rabbit hole, brother.
Bug waves.
That's a rabbit hole that
you laugh all you want. That's real. That stupid idea is real. Hey,
that's just funny. Imagine going to an investor and sitting down. Hey, all right, I want to talk to you about a $5 million investment. Bug waves.
Yeah. You'd be amazed with what you can do with that. Let me throw something up on the screen real quick, Mark. I want to show you something that I've known about for a long time, but it's the first time I have actually run a test. Can y'all see the graph that's on the screen?
Yep.
Okay. Basically, what we have here is there's no thrust being produced. This is just the ion gauge, the vacuum measurement system. This is off, and then as soon as I switch the ion gauge on, it charges the entire chamber with ions. And that's really not important, except that stupid little piece of Kapton that I'm using as a force meter is susceptible to those ions. And Dr. Charles figured this out a couple of years ago in NASA, that the ion gauge itself is able to dump charge into the system. So you actually have energy being put into the vacuum. Of course, vacuum's is really just thin air. So basically, this is the ion gauge dumping ions into the vacuum, and then ion gauges, when they get dirty, you run them. You do something called a degas, and that just supercharges the damn thing, and it runs super hard for about 3 minutes or 5 minutes, and that dumps an enormous amount of ions into the chamber, and then it switches off, and it comes back up, and then I went ahead and switched off the whole ion gauge and everything, so that it just kind of did this, and then it did this. The net result of all this is you be very careful with force measurement if you're using a mechanical force indication system that relies on a strain sensor attached to a piece of Kapton, which is how 100% of all the force meters in the universe operate. So thought I'd show you this because it's a source of error if you don't know what you're looking, if you don't understand it. If you get your ion gauge to stasis and you run from here forever, things are good. But if you just switch on your ion gauge or you punch up a degas, you can get all kinds of false thrust. I mean, this is a millinewton. This is a millinewton of false thrust, which is literally nothing but a bunch of ions dumped into the system. So I thought I'd show you that because that's another source of ways the universe can lie to you that you just don't expect.
Well, Drew, thank you. Thank you.
You're welcome.
And so guys, it's just about 8 o'clock. So, I want to say good night and thank you to everyone for a pretty amazingly successful APEC Open Mic. So I'm going to stop recording.